are we still getting samples?
Because I suspect he has cranked up the selector,
Okay, yeah.
so that when people move around, you can still catch the audio. It's like that.
Jesus Christ.
Because people like move around, right? So
Yeah.
you get it up at such
Okay.
So even in the case when people forget to say something,
It'll mic it.
the mic will catch up. So
For fuck's sake.
as long as we don't get like an audio feedback from the speakers, I think I'm fine.
Yeah, but I am a little bit worried about audio feedback from speakers. Like,
No, it should be fine.
Testing 1 2, testing 1 2. Jesus Christ, that's loud.
But then you stand behind at the level of the edge of the podium and not do something.
Testing 1 2, testing 1 2. Okay, yeah.
And that's usually how people speak, right?
yeah. For better or for worse.
Okay. This is on step.
Ready?
Yes, I mean it's sorry.
Alright. I think that's all the rooms other than, well, John just went to work on terrain. Roxy's working on control end.
Right. So I forgot to mention one thing. Are
Okay.
you contact me if things go wrong?
Okay.
There will be a supervisor here. I will share that with us. And then if you feel like he's being insistent.
Okay.
Are you understand?
No, I can join though.
So sigma.dg / POPL hyphen 2024.
It's fun. Oh no, web browser.
Discard.
Oh, I have to go to Discord.
Discard.gg. Discard.gg / POPL hyphen 2020. Okay, that's the invite link. And then there is a dedicated Q&A forum for the track. There we have listed all the papers.
Okay.
So if there are more audiences that want to ask questions, they can probably ask.
Okay,
Or
so
even like
I-
audience members who can ask them, right? So you might want to make sessions aware that there will be
Okay.
questions and also discussions on each of those. Events.
Yeah.
And on that, on there you can just ask the organizer channel.
Okay.
Type my name.
Okay.
So there are two videos now, Sophie and I. Mostly I'll be on here.
Okay.
So
Wait, I'm still trying to.
Oh,
Let me
okay.
let me just try to open this and then. Um.
are you on the IET guest platform?
Yeah.
Or you can just continue to Discord.
I'm just doing it, but.
Oh, it is going to the web?
Oh, now I'm in the. Okay.
that's a weird thing where it is, yeah,
Yeah.
that's me.
Okay.
So if
Because
you
it's
just
from-
hover on my name,
Okay,
and
okay, okay.
it will send me a direct message, but I would suggest not sending me a direct message because I might be overworded. So ask an organizer would be.
Okay, so I should just, if there's any video problem, I just message
Yeah,
you
just
there.
say
Okay.
incorrectness logic,
Okay.
Mountbatten, AV issues.
Okay. Okay, okay, great.
This
Great.
and someone will come here.
Great.
We have like 6 people around, so one of them should definitely show up.
Okay, sounds good, thank you.
Cool, all right. And I don't know about the AV volunteers, but if it's shut down, we should not have it.
So to plug the.
It looks like there's here.
Oh, nice.
Second speaker.
Yeah.
You happen to be the first speaker this week? Yeah. He's not very good. Okay. Let me know when it's Yeah. Sure.
So it should be sharing the screen.
Is it supposed to just
he was asking whether I have to change something in order for so we can go up. But I'm not sure because now I'm on the. Okay. Are you trying to run a test right now? Yeah. Okay. Yeah. Okay. Is that what you're going for?
Yeah.
I'm going to remove this from the projector again, just because it will simplify it when the person gets here.
Perfect.
There's supposed to be an 80 volunteer here.
Yeah.
I can sit here and fill in until they get here.
I'm trying to locate them.
Roger, I can sit here and fill in until they get here. Are you the regular volunteer? Yeah. You know what you have to do to go volunteer? Okay, good. Good luck.
Sì, sì, sì. Si è visto? No, sì, quando è diventato nero. Sì, 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 no, però quando era nero, cioè si vedeva il mio schermo, non penso ci saranno dei problemi con i lucidi in particolare. I've got one, but if there's enough juice, that looks pretty good. And now I'll turn off the internet. Yes.
Oh. Okay. I don't have an adapter. Like, oh, this works for this? No.
Does it not? There was one here. Oh, that's weird. They put this thing here that doesn't come.
Do they have one of these dongle things?
For the remote.
Yeah. You would think they would, but anyhow. It's okay. Not everybody's arrived yet, so
Yeah,
it's no problem.
That's fine. It's weird that they put this. It's like
Because I'm sure everybody shows up with a setup just like mine.
maybe someone took it.
Oh yeah, possibly yeah.
If we had this.
Yes, it's not what we want.
No. May I put this on your belt?
Sure.
There we go. And
I'll
can just
take this off.
here.
Yeah.
I think should be fine. Okay, there we go. And I'll pin this here.
Nice.
There you go.
Clicker.
Yeah, I'll do it here.
If we don't have the clicker, I'll survive.
I'll try to get one.
Okay, I'll turn this on now. Yeah.
Okay.
They may have to click something.
It's good to know when you're wrong. Oh boy.
You may have to do like mirroring. You probably need to change the mirroring. If you go to the like system preferences.
Let me find where that was. That was.
If you go to the Apple thing, although it's if you just play the slideshow, I think it may work, and you'll see something different here.
Yeah,
You
we're
get-
ready.
You get this.
That's okay. Yes.
Yeah.
Yes.
Wait a few more minutes. We did it ahead of schedule, so that's good.
That's right. Yeah. It's amazing. Oh, we're way early.
Yeah.
that?
It's getting pretty fun.
Yeah. Oh yeah, I'm ready. Yeah.
All right, we're going to get started. Thank you all for coming. My name is Noam Zilberstein. I'm one of the organizers of the workshop. So before we get into the keynote, I just want to say a few words about what this workshop is about. It's about incorrectness. Obviously, incorrectness has existed for a long time. Since programs existed, there have been incorrect ones. But it wasn't until about 4 or 5 years ago that people started to really seriously think about formal methods for proving that programs are incorrect. And of course, all of that started with Peter O'Hearn and a few others. So in order to set the stage, we're going to have Peter talk about his journey, his realization that incorrectness is an interesting and important thing to study. And then throughout the day, we'll see more applications, more ways that people start thinking about formally reasoning about incorrectness in new areas that aren't just about, not just program logics, but also things like types, hyperproperties, and all kinds of other great stuff. So with that, I will hand it over to Peter for the keynote.
Thank you. Okay. So what I wanted to do today is to emphasize a couple of things. So first, when I moved from academia to industry, I bumped into a whole host of new problems. And when I was stepping back and thinking about it, when I grew up as an academic, there was a certain set of assumptions. And the kinds of assumptions you would have coming from some of the greats of program logic. Well, you should write your specification first, and then you should write your program. You should write your loop invariant and then derive all these kinds of things. And then when I moved to industry, this was violently at odds with the way things were working. And they had some reasons that made some sense for why it was violent. And I thought, maybe our assumptions, we should revisit those. Maybe our assumptions are more like religious beliefs than scientific things. So I was thinking about that. And then eventually I got onto this paper I wrote in 2020, Incorrectness Logic. Now, when I wrote that paper, I was really influenced by Hoare. So Hoare created lots of simple things. The one thing he always did in his papers is he tried to write it as simply as possible, so as many people as possible could read it and understand it. And what I didn't want to do is I wanted to remove as much theory as possible from the paper that I wrote on incorrectness logic. And I think I succeeded in that. I don't know that I made any technical contribution in that paper, right? It was sort of a survey piece or a synthesis piece based on a whole bunch of stuff that was sort of known. It's like, well, maybe we could put things together in this somewhat nice way and explain the motivations for why you would want to do so. But as I was writing it, I didn't really think there was hardly any technical contribution. But there's real value, I'm not saying for my paper, real value in explaining things simply and putting things together in a way that people understand. And I thought this is one of Hoare's, the great things that Hoare did. What I thought I would do here now, because I've got an audience of people who are more into the formal side, I want to tell you some of the thought process behind the incorrectness logic that I didn't want to write in that paper. So we'll see if that's useful to people. So, in the beginning, when I was still proving programs correct only, I still love proving programs correct, by the way, and I'm working on that now, but in the beginning, for us, there was some people in London, that's Dino and Cristiano, myself and Hong Suk, working on crazy program analysis. And this is one of our early papers. And this was proving memory safety of device drivers. And so here I was really influenced by the SLAM project. So the SLAM project proved properties of real device drivers. But we worked with Byron Cook, who told us all of the weak points of SLAM. And the major weak points is that SLAM assumed memory safety. So it only proved it, assuming that there were no bugs of the memory safety variety, but there were, right? And so we thought, oh, well, we've got some memory analysis techniques, let's have a go at those. And so then we found some bugs in the drivers, we proved them correct, or free of memory safety errors with respect to certain assumptions. And so this was pretty good. So this exceeded what I ever thought I would do in the practical realm as an academic, because, I mean, there's 10,000 lines of code. Bugs were fixed inside Microsoft as a result of what we found. So I was very happy. I thought this is really good. But then there was this other person we were working with, Cristiano. And Cristiano was very unhappy with these results. Right? Cristiano said, well, how many companies have little discrete 10,000 line programs that are that important? Not that many, maybe Microsoft, but not that many companies. He says, what if we want our program analysis techniques to influence like lots of companies, lots of code around the world? He said, he put it more strongly, this is completely useless, the way Cristiano put it. This was the best possible results that I thought I could aim for, and he said, this is completely useless. And so then he had written on his blackboard at Imperial College, go huge or go home. If you don't have 1 million lines of code that you're covering, then he didn't want to hear about it. Right? So he wanted to get to 1 million lines of code. And he asked me, well, how can we get to 1 million lines of code? And I realized that the big problem in applying these techniques was that we need to discover a precondition when we're analyzing a procedure in order to get to the post. And usually the human discovers it, or we do it in some top-down way. And then I said, well, what we need to do is we need the analysis to discover the precondition, then we can find a post. Then we'll be able to make a compositional program analysis. And so I hypothesized that we'll get something running on big code. And we did, and okay. So by abduction is one way to forwardly analyze the program and throw some information back to the pre. You get a pre, which is going to guarantee memory safety under certain assumptions. Then you get a post. And this ended up giving you a way to have a very scalable program analysis. And so then we published it in POPL. And the POPL referees loved it. And we emphasized the scalability, which was there. And we emphasized that we had proven memory safety with respect to assumptions of a certain number of the procedures. We also found some bugs, but we didn't emphasize that. So this was all good. So writing a paper for the POPL audience. So this is even one that the 10-year retrospective award from POPL. I don't know if it was for trying to prove things, but we thought that the POPL audience liked this aspect. But then when we went out and we started talking to other groups of people, we were forming a company based on this because finally it could scale. What people got excited about wasn't proofs of memory safety. Like Dino used to give a demo. Dino would, at the start of the talk, run on OpenSSL. Because it was a scalable program analysis, by the end of the talk, he would run it on OpenSSL. By the end of the talk, we had analyzed the entirety of OpenSSL and found 72 memory leaks, potential memory leaks. Then, on the spot, he would fix a memory leak and rerun the analysis, and within like seconds, it would confirm that this fix was okay. So it was incremental. And so then you could see that it was, maybe we could put this into the software development process. So people loved the scalability and the incrementality of it. So much so that the reaction in other audiences was quite different. We gave talk at the Industrial Security Conference, and when he did this, somebody in the front of the audience jumped up and cheered. Right? They said, "Yay!" Because they couldn't believe that with all these formal methods, people are all of a sudden doing things incrementally. So that the fastness was very important. The incrementality was very important. So we made a company. Eventually, the company was acquired by Facebook, and we went to work at this company, Facebook, and there's this hack logo on the floor or at Facebook outdoors. But why did Facebook decide to buy Notice? we had program verification people going into the company with this emphasizing hacking, right? They loved the scale of Infer, the fact that they made us, when they interviewed us, they made us run it on the Android OS, and it completed. Just that it completed, they were amazed because many tools don't complete. It was incremental. They could see, ooh, this is going to work for pull request-based commenting. They could see better than us. They hated giving bug lists. They had tried many static analysis tools that gave bug lists. This was always a failure mode. The developers hated it. It did find real bugs. So we ran it on some internal Facebook code bases, smaller than the millions. And one of the Facebook code bases, it found some bugs. And these bugs were in a code base that happened to have been written by hero programmers inside the company. So the people interviewing us thought, this is hilarious, right? Like, this tool has found bugs in the code written by the hero programmers. So then they're very excited by that. Apparently they liked me, Cristiano, and the team. What they didn't comment on was proofs of absence of bugs. They absolutely didn't comment on it, right? We emphasized it over and over again, and they said, okay. But when we showed them bugs of the hero programmers, then they were extremely excited. So I worked for a while, right? We worked for a while deploying Infer. So I hadn't decided I wanted to work on under approximation or anything at this point. So then I worked for a while. I was the manager of the Infer team. Somebody had to manage the team. That fell to me. Then after about 3 years, I was getting extremely bored, and I wanted to work on technical problems. So we arranged for me to move to the to the engineer track, and somebody else to manage the team. And I said to my manager, who's a VP, Brian Sullivan, okay, I'm giving it up. And so for my first task, I'd like to try making a concurrency analysis that can scale to people in the company, to work for the people in the company. And I wanted to prove some code. He said, that's so good. This was really great. He wasn't saying, what was really great is he wasn't saying, what's the return on investment? He said, well, that's a hard problem, but the worst would probably be useful. Go for it. So I had my goal. I wanted to prove hundreds of thousands of lines of code race-free in the Android app at Facebook. So that's what I took as my goal. So I didn't want to do a 10,000 line device driver. Now I wanted to do concurrency proofs of hundreds of thousands of lines of code, hopefully millions of lines of code. So I thought this was a good goal. And I was very charged up about it. And the context at the time was this. So one of the important papers on race detection was by Engler and Ashcroft. And we all know that Engler is very good at, Engler's one of the people behind Coverity. He's very good at analyzing systems programs and finding problems. Now, they found 3 race bugs in Linux, right? This was a good paper, but there's many more than 3 race bugs in Linux, right? They're missing lots. If I worked on this problem at Facebook for a year and found 3 race bugs, I might have been giving my marching orders, right? This wouldn't be good enough. They're great people, but the reaction of this by people in industry, other great people are Sarah Brandy and colleagues who made this dynamic race detector. The reaction in the community was that static race detection is too difficult. We need to go dynamic as a consequence. So they made this dynamic race detection, which is very useful and is deployed in production in a number of companies. And it's called Thread Sanitizer. And so that was the idea. And so, of course, so for me, this is no problem, right? It's like, okay, so everybody thought it's too difficult, so why not have it go, right? After all, we had concurrent separation logic in our back pocket, and I was very cocky. I thought, I think I've got to go for this problem. I don't care that people thought it was too difficult, right? Concurrent separation logic. I think I can scalably reason about code. So concurrent code. So I spent some time, right? What I did is in industry, when you attack a problem, you don't just build the analyzer. You need to understand the context. So I stared at thousands and thousands of lines of the Java code, the Android code of Facebook, try to understand its character, and then try to figure out what would a really good prover/analyzer look like for this style of code. I did mental proofs about the code. And these mental proofs means I sketched out the program logic. I decided that 95% of the code I could knock it over with something called fractional permissions with concurrent separation logic. I I designed an algorithm, a pen and paper algorithm for discovering all of the invariants. The other 5% was very fine grained concurrency. And I thought, I'll get to that later, right? I want to get that 95%. That'll get me to my hundreds and hundreds of thousands of lines of code. And I started writing a prototype. And this was very, very, very fun. So the kind of thing I did in my prototype, although I had an algorithm to infer what's called resource invariance, I didn't implement the algorithm first. The first thing I implemented was how to find some dead obvious races and report them so the programmers understand, because I realized that, well, if I'm ever to succeed deploying this, I've got to have good error messages, number one. And number two, I, as a theorist, I'm a lot better at figuring out how to do an algorithm for proof than I am at figuring out how to give good error messages. So I thought, well, let's concentrate on the thing that I'm not that good at, giving error messages, before the thing that I'm better at, which is algorithms for doing proofs. So I decided to find some obvious races where you've got to write outside any sync. Forget about what blocks, but just any sync. And so in the first case, I've got the true positive self race. If I run that in parallel with itself, right, it's going to be a race. The second one, if I run this in parallel with itself, it's not going to be a race. So I would want to figure out things like that. The third one, it wasn't that trivial. So I looked for, I wanted accesses that are syntactically identical in two threads. So I didn't want to do lots of alias analysis and things like this. Syntactically identical accesses in two threads, which would tell me obviously there's a race. The third case, we would have syntactically identical accesses, but it happens to be freshly allocated. So in the third case, if I run that with itself, you're not going to get a race, right? You're going to get new. So you had to take care of some extra things. So it's not quite as easy as I was saying, but fairly easy cases I try to get. And so I was finding things in the Android code base based on this. Then, and I was having the time of my life, right? So because I was a professor before going to Facebook, I never wrote any real code, right? So I wrote, the only code I wrote was for the programming language classes. Like I would write an interpreter, give it to the students, ask them to change it. But I never wrote any code that somebody else used, right? And I didn't know really, I'd never done any software engineering. So this was really fun because this was my first software engineering. And I got to only 1,000 lines of code, not very much. So I was sort of celebrating, oh my God, I'm getting to 1,000 lines of code. And this was really fun. I was writing in OCaml, which is an absolute pleasure of a programming language, right? Functional programming, the most beautiful type system. Now all of industry is finally catching up with OCaml, with all these programming languages that are very much like OCaml with different syntax. But then, this fellow, Sam Blackshear, who was mentoring me, I was his mentor when I was a manager, that when I switched to be a programmer, he was my mentor because he knew how to program, right? And so he was my mentor. But then we used to write updates to the Android community at Facebook, which is a couple of hundred programmers. And in his update, he said, there's this fancier concurrency analysis checking that the classes marked thread safe are actually thread safe. And I took this to mean if they say they want this class to be thread safe, it means all of the public methods don't race with one another. That's what I took that to. That was the theoretical approximation of that concept of thread safe that I was taking. And people started asking questions, right? Like, will it be recursive? They were asking, is it going to be an interprocedural program analysis in our terms? And this is, well, there's some reasons, but they needed it to be interprocedural or it was a non-starter. So when Sam asked that question, I said, oh shit, right? Because when you're trying to do something, like I wanted to make a proof for hundreds of thousands of lines of code, and I thought, this is very hard, but I thought I could get there in about a year, right? I thought I could get this really good thing. My plan was to get there in a year, and then they're saying, we need this now. And I said, oh my God. And so then I didn't respond to any of the first things people said, and I was hoping that they weren't going to say anything else so I could get back to my nice plan of making my concurrent separation logic proved, right? Then I started getting other messages, like this was from a fellow in New York, and he says how he heard we're working on this, it could dramatically help us in our plans. And so then what am I going to do? Am I going to tell them no? But on the other hand, you've got a team, they were working on something that's important. They needed to take the Android app and convert it so that it was multi-threaded in order to speed it up. Now they're taking a huge sequential code base and converting it to be multi-threaded. Now guess what? There's going to be tons of data races if you try to do that. And their only way of dealing with this was to mentally walk through the code and try to figure out. So it was problem. So they needed this. So then I can tell them, no, I'm not going to help you out because I've got to make my people approver. Or I can say, well, for business reasons, I should help them, right? Because their problems with it. But then there's the other thing is, if you ever try to deploy static analysis to people, usually, at least in the contexts that I've been in, their first reaction is, well, I'm not really sure. I've heard that this is quite noisy stuff, right? And then in this case, they're saying, we want it. So it makes sense for the analysis experts to, if you keep saying, we want it. Okay, let's try to give them something that's useful to them. Now I realized I could not make my prover in their time scale. So their time scale was they needed this in months, not a year. And so I pivoted, and I talked to them about what they needed. And two of the important things they needed is, they said, we don't actually need you to prove the absence of all bugs. Just find a lot or most of the bugs, and we'll take responsibility for the rest. Speed us up, they're saying. Is it, don't worry about fine-grained concurrency. That's only a very tiny amount of the code. The experts will take care of that. Find all of the zero-base bugs. And so we made a program analysis, which is actually not that easy, not a completely easy program analysis, and it tracked things. And it did this kind of race detection. And an example of what it did is it went through all of the procedures, and it would make a summary of each procedure. And the summary information would say, at each program point, if there's a data access, and what the access path is, the syntactic access path, whether a lock is held at that point, if it's on the main thread or not the main thread. And so it then would look at all that information and then decide, does this mean it's a race or not? So what we did is first we make the summaries, then we compare the summaries and decide whether there's races. And so in the cases of the blue, so you've got a write on the main thread and an unprotected read off the main thread. So if we've got a write on the main thread and the other one's off the main thread, that means they can run in parallel. And if one's protected, the other's unprotected, that means they can race. So then we would report a race in this case. But the interesting thing here that I'm pointing out is first, make summaries. Second, make choices. But the whole design of it actually used an abstract interpretation framework inside of Facebook that this fellow Sam Blackshear had made. So I wrote a little abstract interpreter. Although I wrote the little abstract interpreter, it didn't conform to like a soundness theory. It used like, we had a wide knee, we had a join, we had this, but it didn't satisfy the properties that you need to get soundness. And it was easy to make false positives, so it's possible to make false positives. And so, for instance, we didn't even track the identity of blocks. We just said, oh, is there any sync, not lock? So this one, there is a race between those two because those are different locks, so they don't exclude one another. But we wouldn't find it. So there were lots of artificial false negatives. So there were lots of artificial false negatives. Now the analyzer experts, besides me, were really, okay, I was irritated by this, but the analyzer experts were even more irritated. So they started to change the analyzer to make it closer to the sound. So somebody implemented an alias analysis. Somebody implemented an escape analysis. And when we put these into the analyzer, then we get huge blizzards of false positives. Right? So then we say, okay, let's take those out of the analyzer. So then we put it in production, the one that didn't have the soundness there, we put that in production. And lo and behold, it worked incredibly well. I'll come back to that. It worked incredibly well, and it found an incredible number of concurrency errors. It helped them the programmers take the code and convert it to concurrent code and get a speed up. And so this was a very successful project. So if you remember back to the Engler results, they found 3 race bugs in Linux. Like we found 2,500 race bugs within a year with this, right? This was, This was running scalably, running in the continuous integration system. This was a very successful engineering project. But one thing we did when we reacted to the irritation that it doesn't have a theorem, we tried to make it sound over approximate. Then one day, I said, stop this. We've got an analyzer that's effective in practice. We're trying to change it so that it conforms to the usual theorem, and that's making the analyzer much worse. So why don't we change our minds around the theorem and make that fit the effective analyzer rather than the other way around, rather than make the analyzer worse, make it fit the theory. And so I said, our theorem should be that there are no false positives relative to certain assumptions. And the certain assumptions had to do with some things that were happening in the client code that we were applying it to, not infrastructure code. But it boils down to, we were trying to prove a theorem that the analyzer could be an under approximation of the over approximation. So the over approximation documented certain assumptions, and then you would have an under approximation. And it turns out that this theorem was never true of the analyzer, but we took it. This is much more important. Like, the theorem to bless the analyzer afterwards is much less important than the false theorem which influences its design. And so we made design decisions that were consistent with this theorem. And we made a baby version of the analyzer which had it, but the real analyzer never really had this theorem. But this theorem guided the design. So an example is, if I've got x.f and it's owned, so it's local, then I assume x.f.g is also owned. So it's actually false because of the way things can escape to other threads, it's actually false. So we took that as an assumption, and that assumption, which made the analyzer easier, is consistent with the theorem. So the theorem drove us to make certain choices in writing the analyzer that we wouldn't have otherwise done. So that was really interesting. So thinking about this in hindsight, so we wrote 2 papers. So we wrote a practical paper about the analyzer. The first one, which had a very hard time getting in, but the second paper in POPL proved the theorems about an idealized version of the analyzer. The POPL audience, the POPL people liked it, and they made comments like, "I can't believe you were able to prove any theorem at all about an unsound analyzer." And this sort of brought I thought, why are they saying this? I mean, it's just an under approximation of an over approximation. The kind of thing you should do, use the approximations, and it is. But I realized that a lot of people thought it's just unsound is bad in their minds, right? It's not like there's something to say about the unsound analyzers. There was an idea. It just means it's bad. And I was just scratching my head about that. Maybe we can try to do something about that. And the other thing is that although these papers got in, they didn't generate that much attention, and I was wondering why. And this second paper, although it did prove the theorems, I mean, it's complicated. So it's complicated in details. So we were trying to somewhat match an in-prod analyzer. So it's very hard to take an analyzer that has real impact in practice and write an elegant paper on it. Let me put it like this, I don't know any such papers. I know loads of elegant theory papers that aren't about things in practice, like Hoare's logic. If you don't mind, Cuso 77 is one of my favorite papers of all time, right? So there are theory papers that are very beautiful, and then there are the practical analyzer papers. There are almost none of these to me that are beautiful. I think it's just very, very, very hard to do, and we were in that. We were there. It was very hard to do, so I thought, going forward, maybe I can try to do something simpler and not do something about in-prod and be able to get a message across a little bit better. Okay. So this gets us on to incorrectness, logic, and friends. So I was wanting to do something like this, and I got a prod. And so the prod was, so Derek Dreyer and others were in town when we were working on a program analyzer to find memory lifetime errors in C++. And Sam Blackshear, my former mentor, had made a version of this based on the lifetime checker, the borrow checker from Rust. He tried to import those ideas to C++. Blizzard of false positives again, right? Like the Rust idioms just didn't fit the C++ idioms. And so I reacted very badly to this, like in 2 ways. Like, why take the least successful part of Rust and import that to C++? But also, the blizzard of false positives, I didn't like it. And this original bi-induction analyzer that we took into Facebook, I had said many times, why didn't we make an under-approximate version of this? And nobody ever listened, and so I should have done it myself. But then we're in the room, and one person, Jules, was in the room, right? And so then we said, we need an under-approximate version of Infer to go after this problem. And he went and he just implemented, without telling us, he just implemented a version of this, and this worked pretty well. And so this got us going, and then it was inferring 4 triples, but the 4 triples were found by under approximation or something that we didn't know. And so then we were thinking, well, we should maybe try to understand the meaning of those triples, which this analyzer seems to work fairly well. So several of us started thinking about this, and there were several proposals. There was an interesting proposal, which will come up later, from Derek and Rob Young when they met us in Lisbon at POPL 2019. But so I was thinking about this, and so I discovered a couple of things which did or didn't match the analyzer exactly, but I thought we're getting in the direction of being very beautiful. This isn't what I wrote. What I'm going to tell you now isn't exactly what I wrote in the POPL paper, because I had this motivation for what to find, and then I found it. Then I took the next step is like, let's write a paper which doesn't uncover all of that, but just writes it in a way that like as many people as possible can understand it. But now that I've got this kind of audience, I want to reveal that part. And so to reveal that part, I think we have to look at the beauty on the over-approximate side, right? So the beauty on the over-approximate side, so there's the horse triple, right? And there is, well, I guess I would associate that with Floyd, although I don't think Floyd ever used the word invariant. But a superset of the states at each program point, let's call that an invariant. I don't know who used the word for that, but Floyd had that idea in his paper. And then to show that something is an invariant, it's sufficient to find another invariant less than it, right? So if you've got your postcondition Q, you find some stuff that implies Q, with the rule of consequence down at the bottom is the way you say that. You might associate that. But Floyd had these ideas that the over-approximation at every program point. And this is sufficient to prove a program. Very, very beautiful to me. So simple. And then the third part of the triumvirate of beauty, which is Floyd, Moore, and Cousseau, which is that so from the transition system I can make a continuous function, Scott continuous function on a lattice, which just keeps gathering more states. And the reachable things are the least fixed point. X is an invariant, just says that X is bigger than the least fixed point. And so then, we can say this for like lots of arbitrary lattices, not just for this. We can say similar things. So then if we have F over hat is an over approximation of F in the pointwise order, right? Then if I have, if I just calculate the least fixed point of F over hat, however I might do that, an abstract interpreter does that, then I know that that's bigger than the least fixed point of F via monotonicity and the pointwise order. Then I know that that's an invariant of F or of the transition system T. Oh, and so calculating this least fixed point least fixed point of F bar, that gives me a way to prove my program, right? Now, it doesn't give me a way to disprove the program, right? That's the source of false positives. But all of this is just so simple, and so I like these 3 things I like, right? Unambiguously, I like this stuff. So I didn't say this in the POPL paper, right? Now, so let's just try to redo that with under. So then I just flipped the subset around to say, well, we're going to under-approximate the post, right? There's an equivalent way to say it. And so people have taken this equivalent way to say it, which is that everything in the post comes from something in the pre. People think that this means it's about backwards reasoning. But they couldn't be more wrong, because forwards predicate transformer exists, backwards predicate transformer doesn't. There's a category error people will make, which is states versus predicates. On the predicate level, this thing works beautifully for forwards reasoning, not as easily for backwards. So this is not a backwards reading formalism, but anyhow, so backwards predicate transformer doesn't exist. And Hoare's assignment axiom doesn't work. You have to use Floyd's for that reason. So instead of invariance, let's say that a subvariant is a subset of the states reachable at every program point. Then to show that Q is not an invariant, to show that it's incorrect, it's sufficient to find a subvariant which shows that it's incorrect. It's like the testing idea. We find a way to just show that it's incorrect. And it's the same to say something with the under approximate triple. So these blue bits are what's different from the beautiful bit in the previous slides. The subvariant, and the subvariant gives us a way to disprove, where the invariant gives us a way to prove. Then we can do this. We can do all this. We can say X is a subvariant if it's a subset of the least fixed point. This isn't complete dual stuff. If I was to just dualize, I would say X is a subset of the greatest fixed point, right? Like if I'm dualizing, you take least to greatest, but you don't want to do that. The meaning is calculated with the least. So although there's some duality, the theory is not entirely dual, basically because of that. So X is a subvariant. The fact is that if the least fixed point is not less than X, then it's not an invariant. So that gives us a way to disprove. Now, if the least fixed point of the under approximation is less than X, it doesn't prove that it's invariant, right? So now it's the source of false negatives, not the source of false positives, right? So I'm not saying that this is as beautiful as the previous one, but this is why I worked. It was, things are lining up here. Things are lining up here like I wanted them to line up, right? So there's one thing is that Joule prodded me because he had an effective analyzer, but this doesn't necessarily fit perfectly the effective analyzer, but it's lining up with the previous theory that I liked, so I have an opportunity to do that, where we sort of failed in the Racer D theory papers to explain it so that just a lot of people would understand it. I thought, okay, now we've got things lining up. And then I took a further step of forget all of this and explain it to people without knowing this, right? But this is what, for me, made everything line up. So, oh, this is very, there's lots of other things to say. But now if I compare the under and over approximate semantics, then I get a diagram like this. And that's the least fixed point of the concrete semantics if F is continuous. Now you see right away that this is just like, oh, I can stop after finite unrollings for under approximation, right? Well, that's immediate from that diagram. If I stop there, it's not sound for over approximation. This is but it's just immediate from there's lots and lots of things you can see from this abstract perspective very simply. And so that you know is true, so this is just confirming that it's true. So again, this is lining up. There's much more I can say about the things like this. But I want to move on to the kind of thing you would like to do, which is to use all of this stuff to build I want to build an interprocedural compositional program analyzer. And I want to make a compositional program analyzer, which means it analyzes procedures in isolation. I want to do that because, at least in theory, because if I can do that, then I can run it at PR time very quickly. I can put it in the CI system. If I make a global program analyzer on 10 million lines of code, even if it's linear time, no, I'm not going to be around. It's going to be very difficult to put that in the CI/CD system. So let diag be the diagonal assertion. So it's like true, but it records some things. Then if I take the strongest post condition, then this gives me a way to describe the relational meaning. And so for instance, if we've got that example, then the capital X is recording the initial value. Then afterwards I get X equals X plus 1, but X is even. But I don't get anything for the else branch because divergence, right? In this under approximation. So we don't get anything in the else branch. So that calculates that. And so suppose I have something that's an under approximation of post, which is what you want, an under approximation of correct interpreter. Right? Then we can have, let me say the words transition subvariant. Podolsky and Rubelchenko talk about transition invariance in their work on determination proving. So this is like a transition subvariant is what it's discovering. That we need the post. So that's cool. And so all of this is theoretically, it could be the basis for a compositional interprocedural under-approximate analysis. It's not what Joel's tool Pulse does, and I'll explain that in a minute, but it could be. So this is quite interesting. So, oh, did I mean to have that as my next slide? Perhaps I did. There's another thing I could have done, and this is what was suggested by Dreyer and Young. But it turns out that Godefroy et al. Had it in Must transition years ago. But anyhow, instead of under approximating the post, I could under approximate the pre, right? And so there's something called predicate transformer, which is the pre-image of a relation. And so it's not the weakest precondition, it's not the weakest liberal precondition, it's what's called the weakest possible precondition. I think Hoare called it that. But it's like take the post of the inverse of the relation linear of a program. So an equivalent way to say what this triple means is that everything in the pre can reach something in the post. But it might reach things outside the post too. But everything in the pre can reach something in the post. Now, this, although the equivalent formulation seems to, in the states, encourage you to think forwards, if you think in terms of predicates, well, there's a backwards predicate transformer, namely P, of course, namely pre, which corresponds to this. There's no forwards predicate transformer for this. Okay? The fact is that the fact down there is that it's the same as post on the reverse program. And this means a lot, but maybe not everything. And I think the next talk will be talking something about this. But not everything translates for the under approximate triples, but a lot of it does. So we could go forward. We could go back. This is where that's quite interesting. So this is where I start thinking, okay, we could do this, we could do that. I'm not sure which is better. I'm starting to get a bit puzzled, but at least as a theorist, I know I could go forward and I could go back. And so then there's something quite interesting which has come up, which is now we're getting beyond my original motivation for some other stuff. So say that we've got a both ways triple if it's sound for the under approximating the post and sound for under approximating the pre. So for both. Now this gives what I'm going to call a both ways triple. Azalea observed this. Pulse actually is compatible not only with the forwards under approximate triple, but also with the backwards under approximate triple. So all of the steps that Pulse does, the under approximate version of Facebook infer, is compatible with both of these things. And so she made this observation, and we say it in this paper here. So this is quite interesting. Pulse is not corresponding precisely to this under approximate theory that I said, but even a tighter version of the theory. What's going on there? Well, what's going on there is that, oh, I didn't say this part. One way to get a both ways triple is to first start from true, or the diagonal relation, under approximate the post, then go back and under approximate the pre. Then via these two steps, you'll get one of these both ways triples. You'll get one of them, but this is not at all the way Pulse operates. So the way Pulse operates is using this thing, abduction, right? And so what abduction does here is it goes forwards, and as it goes forwards, when you hit Boolean conditions, it records the Boolean conditions in the pre while it's generating Pulse. So it's not literally a forwards predicate transformer, but it's something that goes forwards and it records information as it goes along. Pardon me. And so, for instance, if we've got an assumed statement, which is like the branch of an if, and we've got a precondition P, it records B, little b. Now I'm going to rewrite it with capital letters. It records little b as something to throw back to the pre, and it carries it on to the post. For the plus statement, which is like I've got two branches of an if, it union, so it might generate two of these triples, not just one of these triples. So is doing, what's going on here. So as you're going forward, you're shrinking the precondition, and you're generating many such preconditions. So now if I try to just think in a very theoretical terms, why would you be doing this shrinking the precondition? Think of this backwards under approximate triple. The backwards under approximate triple, it doesn't have a forward predicate transform. Right? So given a pre, there doesn't necessarily exist a post. So what Jules is doing in retrospect is this. What he's doing in retrospect is he's got the pre, but there is no post for the pre. Right? So what he does is he shrinks the pre so that there's a post. Shrink it so that there's a post. Shrink it. So that way you end up in one pass, instead of go forward and back in one pass, you end up getting a triple, which works for the backwards predicate, the backwards under approximation, as well as the forwards. So I think that explains sort of the fact of the matter of what Pulse is doing. We did it with, we did this abduction thing. We just did it. And so why are they doing that? My way of trying to explain now why you do that is if you do want to have this backwards under approximate triple, then you're forced to. You've got to shrink the post. In the old over approximate world, infer was working for the over approximate triple where for safe preconditions only. So again, when there's a pre, there's not necessarily a post. So we're using it. We're forced. We're using abduction to find the safe pre. Here you are using abduction to find the pre when no post exists. Now, there are ways to break the forwards under approximation and the backwards under approximation. And sometimes you might want to do that, but in Pulse right now, it happens not to be doing that. So I think I would like to do is good, really. What I wanted to do is to dig. You see, I'm thinking in terms of predicate transformers in most of the motivation and a lot of the things, not necessarily in terms of core logic. So core logic is a good way to explain what the principles of the reasoning are. But really, because I was thinking about program analysis, it's mostly predicate transformers that I was thinking about. Now, we've got this backwards way of going and this forwards way of under approximating. And I see now 3 ways, based on just what I've said right now, to make an interprocedural compositional program analysis. One is this abduction way. The other is with the forwards predicate transformer, generate the post starting from a diagonal. I could do the same thing with the backwards. So this is where there's going to be other talks and there's other people in the audience. I'd just like to confess that it's not so much that I think I don't understand the theory. I think the theory's all, it's just you put together a bunch of stuff and then you try to organize it in your head. There's no difficult math here. I mean, 0 difficult math. Right? But what I don't understand is the ramifications for program analysis of what are good ways to put these things together. So Pulse exists, right? I could now say that I could have made different choices and made other program analyzers that are a bit different. And well, I don't really understand which ways would be best. So I feel like over approximation has been hugely studied, right? Loads and loads of papers, loads and loads of smart people. Under approximation, at least not concrete. So not concrete under approximation has been studied, but much less studied. So we just don't understand it as well because we haven't explored it as much. So I'm not talking about understanding the meta theory. I'm talking about, it's like understanding the grammar of a language and being fluent in the language. So maybe we understand the grammar of under approximation and we're not so fluent in under approximation. So gaining the fluency is where I think we have a lot to learn. Okay? Okay, I'm going to stop there. You picked a good moment to switch off. Oh, no more slides. No.
Great. Yeah, so now we can take questions. Looks like here.
So I was very...
You're very what?
No, it's my microphone that doesn't work. Okay, so I was very intrigued by your theorem on POPL because you said it's an under-approximation of an over-approximation. And I think it's not so true, because if you do further over-approximation and you introduce the true positive in this over-approximation, then when you do the under-approximation, the false positive, excuse me, you might find this false positive. So it's more subtle. What you do in the over-approximation does not influence in any way the under-approximation, and then when you do the under-approximation, it doesn't matter which over-approximation you have done. An example would be you have a buffer. You can over-approximate the value that go in the buffer because they don't matter on the incorrectness of the access. And so it's not over-approximation on under. It's some over-approximation that don't influence the under, and then a true under which is not influenced, so which is a true under of the semantics. So I think it's rather subtle.
I think it is subtle, and my explanation of it is under. First it's over, then it's under. It's an under. That's why there's no theorem in the paper which says that, and so that's my way of explaining what the theorem should say. But what it does is it takes a program, replaces the program with non-determinism in certain places. So I'm saying that step is over approximation. Then the resulting program really does an under approximation. So that I don't know if what I just said just agrees with what you said, but
and the approximate analysis can have false positive with respect to the concrete.
oh yes,
Oh,
yes, that's correct. Yeah.
And the second point on relational and the post-word give, this exists since 81. And it was implemented by Alvax in the polyhedra analysis by doing a forward analysis and then a projection, you get backward information, and then you can iterate. And maybe you could try to do this iteration to get more precision.
Yeah, I believe. Like, we haven't even implemented one of those in the center approximate setting. I believe this. I think this agrees with me that we've explored much more of this in the over approximate setting. But I hear what you're saying. For everybody, Patrick's saying if you go back and forth between the under, between the back and forward and back and forward, then you can do this to increase precision.
Yeah. Okay, thank you. That was my remark.
Okay.
Otherwise, it was good work. Yeah, don't worry.
We have more questions.
Hi. You in your language for the incorrectness paper, you always use assume statements, right?
Yeah.
Why do you use assume and not assert?
Oh, that's a very interesting question. So I'm saying, like in the code assert, I think it says assume this then error. Right? So I think now assume is just it's just to make the if statements work. Right? So that's why. Now, but there's a more comical thing to say, which doesn't have to do with POPL papers, that programmers often use assert like we use assume. So the Facebook programmers will say, assert main thread. And then if the analyzer says, well, you're not on the main thread, no, but I put an assert there because I'm assuming. The programmers very often use assume. Right? If I can encode assert. I don't think I can encode assume. It's all, the programming language was just trying to, just for theoretical minimalism.
Hey, Peter.
Greetings, Alexander.
So I was hoping you would have circled back to the concurrency question. So now from the incorrectness perspective, do you think it will be easier to build tools for concurrency?
I'm not sure. Well, Racer D is such a tool, and Azalea has all made a concurrent incorrectness separation logic, which I think mostly corresponds to it. So I hope so. I'm not too sure about like fine-grained concurrency, because you end up getting into the details of the interleavings, or worse, worse than interleavings for weak memory. So I don't know if there's any free lunch there, but let me put it like this. For catching a lot of concurrency errors, there's scope for tools that are very scalable and catch a lot of errors. Eraser D just completely proves that point.
Any more questions?
In the last slide, very interesting last slide. In the last slide, there is a problem with the non-termination because it's not symmetrical. So in a sense, it does not take non-termination into account, and I think it should be possible. I don't know why. I'm not able to do it, but yes, so when you have the relation, you could have also a relation to non-termination, and I have the intuition it's possible to do it both ways also, but I'm not sure.
So in fact, I think there's going to be a talk today on proving non-termination. So hopefully that will confirm your intuition.
Any more questions? Okay, great. So let's thank Peter again.
Yeah, I think should be better. I think it's sharing the screen. Yep. No problem. Yep.
Yeah, should work. And then I'm gonna put this
Maybe here.
and then I turn it on, so I'm
Okay.
Okay, so our next talk is going to expand a little bit on some of the things we heard towards the end of Peter's talk about different approaches to correctness and different approaches to, correctness and incorrectness. So we have Flavio Ascari here, and go ahead.
Okay, so yeah. This talk I'm talking about a comparison of problem logic for correctness and incorrectness, because as Peter said, we had lots of program correctness in the past. We had lots of program incorrectness logics in recent years after his seminar work on incorrectness logic. And so what we did is try to compare some of these approaches in order to give some, to sort them and to have a better idea of what can do what. And also, I mean, this is the first part of the contribution, a taxonomy, in which we consider some of these program logics, we organize them and try to compare them. And then we also define sufficient incorrectness logic that is a proof system for the backward under approximation condition that Peter mentioned. And we designed this new proof system because we had a very precise goal in mind that was a sound and complete proof system with the idea of a backward analysis to match the backward under approximation idea. So just to briefly start and to fix the notation, we have OR logic for program correctness. I use this notation, the semantics of R, for the post condition of the program R. So oral logic can prove correctness, but saying that Q, the post-condition, is an over-approximation of the program semantics applied to P. Dually, incorrectness logic takes the same program semantics applied to P, but takes Q as an under-approximation. And in this way, it can prove real bugs in the program, and so it can prove incorrectness properties. So, incorrectness logic gave a new perspective of program incorrectness, but as I said, there was some work. There were many works on program correctness before, and there have been many works on program incorrectness after. Here there are some. I just want to, for instance, here we have the backward under approximation that he mentioned, that has a very interesting meaning. That is backward under approximation type of ERQ means that any state, each and every state in P, has an execution leading to a state in Q. And this is interesting because if Q, for instance, specifies an error, this means that every state in P is a witness to an error. We don't know exactly which error in Q is reached, but for every state in P, we know that it leads to one of the errors. And the importance of this property was, for instance, also recognized by Outcome Logic, published, well, actually, now it's last year. And, so this is one of the things we studied, and they say the condition we designed the proof system for in the second part of the talk. So the first part was basically the definition of this schema, and so we have oral logic and incorrectness logic that are well understood as over or under approximation of the forward semantics of the program. But then we also consider the backwards, what we call the backward semantics, that is the weakest possible precondition that Peter mentioned before. And so we had here, this is the backward under approximation, or as we call it, sufficient incorrectness logic, because that's the name we gave to our proof system. And this is the backward under approximation condition. And lastly, we consider the backward over approximation condition, and we understood that this condition is actually the necessary precondition proposed by Kuzo et al. In 2011 first. And the idea of the necessary precondition is that whenever P is violated, then Q cannot hold at the end of the program. This is because P is necessary for Q to hold at the end, so if it is violated, Q does not hold. And this can be used, well, in a sense, both for correctness and incorrectness, depending on how you interpret P and Q. And so, for instance, if Q is the set of safe states, if P is violated, you have incorrectness, because if P is violated, you are not in a safe state at the end. And so it can be used also in this way. So we defined this schema. We filled the gaps because in the original formulation, it was not entirely clear that necessary conditions were defined by this backward under approximation condition. And so we use this schema to drive a comparison of these logics. And the first thing we consider is the consequence rule. That is the ability to weaken or strengthen the pre and post condition in a logic. And we have that in the schema, the consequence rule follows the diagonal. So we have both oral logic and sufficient incorrectness logic can shrink the precondition and weaken the post. And conversely, incorrectness and necessary conditions have the same consequence rule that is the opposite. So since they have the same consequence rule, we try to compare, for instance, oral logic and sufficient incorrectness logic because they seem related because of this. But it turns out that the consequence rules doesn't really give much about the similarities of the logic. So we have that oral logic and sufficient incorrectness logic are basically not related for a general program R. And we have some relation when R is deterministic. Well, if R is deterministic, the seed condition turns out to be total completeness. And so total completeness implies oral logic, that is partial completeness. And on the converse, if R is terminating, we have that oral logic becomes total correctness, sorry. And this implies sufficient incorrectness logic. But in general, there is no relation between sufficient incorrectness logic and oral logic. And for necessary condition and incorrectness logic, the thing is even worse, let's say. because these are the, let's say, quantified versions of the conditions for necessary condition and incorrectness logic. And as you can see, they are basically the same, but for the fact that necessary condition, the first one is that for all state in the macro semantics of sigma prime, while incorrectness doesn't exist. And these two formulas are basically not related. So if you know one of the two, you basically don't know anything about the other one. So this first result was a bit surprising, but it is already something on the comparison. So what we try to do next is to compare logics along the approximation axis. So we have the two over approximation logics that are our logic and necessary conditions. We compare them, and we found that they are strongly related. That is, a normal logic tripod, here Q, is valid if and only if the corresponding necessary precondition tripod with negated P and Q is valid. And this is a very strong relation. So with this relation, we went on for the under approximation side. So we compared incorrectness logic and sufficient incorrectness logic. And we were a bit surprised to find no such relation. And actually, we didn't find any relation at all between IL and SIL. They are basically, let's say, an IL tripole in general does nothing about a SIL tripole and vice versa. And this lets us to understand the fact that over and under approximation are dual theory only on the surface, but there are lots of things that break the duality. For instance, as Peter said before, the definition of the program semantics is in terms of least fixed point. In both cases, if you over or under approximate, either way, you use the least fixed point of the semantics, and this is something that breaks the symmetry. Another way to see something like this is that if you compose the forward and macro semantics in both ways, you get something that is more or less increasing, but for some, let's say, particular states. And this is clearly asymmetry because both, if the theory were completely dual, you would expect swapping the order of composition, that one is increasing and the other one is decreasing or something like that. But they are both increasing, and so this clearly gives a direction of the approximation, and so it breaks the symmetry between over and under approximation. And we also observed something similar in the context of abstract interpretation, where designing under approximation domains becomes difficult exactly when you take into account the semantics of programs. And so this was the first part of the work on the comparison based on this taxonomy. And then we defined our sufficient incorrectness logic proof system that you can see here on the slide. That is a proof system for the backward under approximation condition. As I said, the motivation for this is that the backward under approximation condition is very important. As I said, it was recognized already in the paper by on outcome logic that this condition gives you an interesting condition, that is the fact that every state in the precondition reach a state in the post. And so this is a way to find actual witnesses that you can use for debugging, because every state in the pre can be taken as a starting point, and then you run the program on this point and you get to a bug. And so we consider this condition interesting. But what we couldn't find was a proof system that was complete, minimal, and based on the idea of doing a backward inference of the precondition given the post condition. So we define this proof system. There's 5 rules that are the, let's say, the bare minimum to have a complete proof system. And then we define some extra additional rules that are useful and can help in doing the analysis. And as Peter said, this has some things in common with incorrectness logic. For instance, well, okay, the sequential rule for sequential composition is the same, but what is more interesting are the 2 rules, these rules for iteration, iter0 and unroll, that basically allows us to do a finite amount of unrolling of the loop and stop, and this gives us a sound under approximation. These rules are valid for incorrectness logic, and these rules are valid for sufficient incorrectness logic too. And so this is a point in common, for instance. But there are other differences. For instance, the iteration rule in correctness logic, the iteration rule is forward, while in sufficient incorrectness logic, the iteration rule is backward. So as I said, we took this validity condition, that is the backward under approximation, and we proved the soundness and completeness of our proof system, and we proved completeness using only the first, let's say, 5 core rules, because these are all the rules we need for completeness. But what is more interesting is the fact that the proof system favors the backward analysis. So for instance, this is an instantiation of the atom rule for Boolean guards. And as you can see, here we have a generic Q, so any post-condition possible. And what we do is that we join it with the semantics of the Boolean guard, the condition. And so we get a precondition for any given post that you have at that program point. Another example is the choice rule, where we have a single post-condition Q. And from that, we infer, let's say, backward 2 preconditions, P1 and P2, and then we join them to match the non-deterministic join of R1 and R2. And this is, for instance, let's say, a difference with respect to incorrectness logic, because incorrectness logic, following its more forward flavor, it starts with a single precondition and derives 2 postconditions for the 2 branches and joins them. Another example of this can be seen in the iteration rule, where Q0 is the starting point of the iteration and is completely generic. Then from Q0, we do 1 iteration of R backward, and we get Q1. From Q1, we do 1 iteration backward and get Q2, and so on. And we join them all in the complex precondition. But again, we started from the single Q0, that is any possible postcondition we care about. And lastly, one of the very important points of incorrectness logic was its ability to drop disjuncts in the analysis. And we argue that SIL can do the same thing. It can drop disjuncts with respect to the backward direction of the analysis. So this is a, let's say, weaker version of the consequence rule, where if you have a disjunct P union P prime in the precondition, you can drop P prime and only care about one of the disjuncts P. Or with the empty rule, we can just ignore completely a path through the program fragment R and ignore it, putting the empty set as the precondition. And so effectively we are dropping the path that goes through the program R. So this is the basic proof system for sufficient incorrectness logic that we considered. And it was extremely important to understand the characteristic of this proof system, and for us to let's say, to really write these things down. But of course, this is not an effective proof system, because in this proof system, we assume P and Q to be a set of states. We use concrete semantics, use concrete union, and so on. And so you cannot, let's say, actually implement this proof system as it is. So what we did is to instantiate it with a formula from a logic reminiscent of separation logic. We actually took inspiration from both separation logic and incorrectness separation logic. And so we gave a proof system for separation SIL. That is, we took the idea of backward under approximation from SIL and the ability to deal with pointers from separation logic and incorrectness separation logic. And we gave a kind of an effective proof system in the sense that here we have that assertions, pre and post conditions are a formula in a logic. And you have that the rules work on this formula and transform them in a way that is, well, not as abstract as using concrete sets. So we took this program fragment from the paper on incorrectness separation logic that basically models the, let's say, the first part. You take a reference to the buffer pointed by B. Then you do a pushback operation on the vector B. And this can, in a non-deterministic way, it can reallocate the buffer underlying the vector B. And so we took this program fragment and we compared what separation C can do with respect to incorrectness separation logic. So incorrectness separation logic, starting from a state where the buffer is allocated, it can prove that we are in a state where X is deallocated. So a use of X after this program can lead to an error. What we did with separation seal was kind of the opposite. We saw that there was an use of X after this program, so we started with the post-condition, specifying that X is deallocated, and we said for the rest of the heap we don't care about anything in the rest of the heap, so we say that the rest of the heap can be whatever. We only care that X is deallocated. Then we use the seal proof system to do a proof that basically guided us with the proof system to find this precondition. And this precondition tells us that you start in a state where the vector V points to a valid buffer, and something else in the state that we don't really care about. And the point is that this precondition is the same as seal, but has a stronger guarantee, because it tells us not that the states where X is deallocated are reachable, but it tells us that any state satisfying this precondition, so any state where V is correctly allocated, reach one of the error state. And so this gives us an actual way to tell a programmer, okay, take one of these states, any one, and from here you can see that this state has an execution leading to the error. We are not the first proof system that is able to prove a triple like this. As I said before, outcome logic recognizes the importance of this condition, and so outcome logic is able to prove basically the same triple, but for some technicalities. The difference we found out with respect to outcome logic is the, let's say, how we use the proof system. So the derivation is different. They can prove the same triple, but we have a different derivation, in the sense that, to our understanding, outcome logic is more forward-oriented. So you start from this precondition, in a sense, and you get, in the end, the interesting post-condition. While, as you can see in this example, the seal proof system does the opposite. So it starts from the post-condition and builds up the pre. So this proof is read from bottom to top. You start with this. You see that you have to apply the atom rule for this atomic command. So what you do is use consequence rule to strengthen the post-condition. So from this true, so whatever is in the heap, you extract something that allows you to apply the rule for this command. Then you apply the rule and you get another post-condition. Again, from this post-condition, you want an allocation. After an allocation of y is allocated. So you extract this allocation from the true, and then you apply the rule for alloc, and you get this precondition, and so on, going all the way to the top and getting that precondition. This is not the full proof, of course. This is just a subset of just a part of the proof, but it's an interesting part because it really shows how the proof process goes from the error postcondition and gets up to the interesting precondition. And so this is, like, as I said, basically the idea of seal, and this is our proof system separation seal instantiated for separation logic. So to conclude, we found in the literature many approaches to program incorrectness. So we took some of them and we tried to sort and compare them, and we used our schema to to try to understand what are the pros and cons of every approach. And then we designed the sufficient incorrectness logic proof system that is, as I said, a proof system for the backward under approximation condition. And here there is nothing new. It was known since at least 2019. But what is new about our proof system, it is complete, minimal, and designed with the idea of backward inference in mind. So in the future, we would like to extend the schema because the 4 main cells are already taken in the schema, but there are lots of interesting logics that are, let's say, in between 2 of these cells. So for instance, outcome logic combines things from Hoare logic and sufficient incorrectness logic, and not only that. And
Sorry, there's an issue with the mic. Can you stay near this and speak in the mic?
Oh, sorry. So we have these. We have, for instance, exact separation logic. That is a combination of Hoare logic and incorrectness logic, instantiated for the separation logic setting. And we have Anter, that is the proof system that Peter mentioned before, that combines things from IL and SEAL that was implemented in Pulse, and many other, and some others. And lastly, we plan on combining IL and SEAL, but in a different fashion than what Anter does, and that is what Peter mentioned before, that is kind of a forward analysis with IL, followed by a backward analysis with SEAL, with some interplay between them also, let's say, in the middle of the analysis. So this was everything I wanted to talk about. Thank you for the attention.
All right.
Okay, so on your previous slide, there is a word missing, very important, because you say the first complete backward, which is not true. WP is also backward, so you have to say backward under approximation.
Sorry, yeah, you're right.
And so my question is, if I take a transition system instead of the language, then I think if you take EL for the transition system, you can take SEAL for the transition system, you can take EL for the inverse of the transition system, and then you will get SEAL.
Yeah, this is, where is this? Okay, here. As you can see, let's say the VPP is defined exactly as the inverse relation.
It's not so clear because I don't know if you mean pre or pre-tilde, which are different.
Yeah, I mean, this is the definition for the backward semantics that we use, and this is exactly the weakest possible precondition.
Because this is true only for pre-tilde, not pre.
Yeah.
Okay, so it's pre-tilde. Okay, so I agree.
Yeah, sorry, yeah, this is a matter of, we use this notation that is maybe not entirely standard. But yeah, this is, our backward semantics is exactly given by the inverse relation of the forward semantics. If you consider the forward semantics as a relation, you take the inverse relation, and that is our backward semantics. So it's exactly the pre-tilde.
One slide you had, there was a comparison on two sides, and it's on the left it said, if you had there it is, yeah, deterministic on the left, you get some correspondence, not deterministic versus terminating. Those are the two choices.
Yeah.
On the right, you said no relation, but is it true that if you had both determinism and termination on the right, then you do get a relationship? Because the quantifiers basically say the same thing.
Yeah, but the issue is that it quantifies on all states in the backward semantics. Okay. And so even if you have a deterministic program, its backward semantics may not be deterministic in the sense that many states can lead to the same output. And so when you do it backward, it's not deterministic. I think you can say something if you say that the backward semantics is deterministic or, well, terminating in a sense because you are going backward. But it's not really a condition that makes sense if you look at the program, the program. I think the backward version of deterministic is like if the function is injective forward, so you can go backward in just one way, but they are not really meaningful notions on the program R, because here the quantification is on the backward semantics.
Maybe it's reversible program. There's a technical definition of a reversible program. Maybe that's what you need there. Sorry.
Yeah, that could work. Thank you. We'll have a look into that.
Okay, I have a question.
Yeah.
So you had a paper a few years ago about how it's difficult to design abstract domains that are compatible with incorrectness logic. Mm-hmm. Do you know if any of those issues are like similar or if they go away when you switch to SIL?
Yeah, that's a very interesting question. Thank you. We talk about that. We started talking about that like actually a few days ago, and we realized that those limitations actually assume, for instance, that the semantics of basic constructs is a function. And this is not true if you go backward, because if you go backward, you have many initial states that leads to the same final state. And so we started thinking about, okay, but if we go backward, we don't have those limitations anymore. And so what can we do? We can design an abstract domain, or we can like actually change our results to take into account this other thing. And no, we don't have any result yet, but it's something we thought about just a few days ago.
Hi, very nice talk. I have a question about the part about separation logic. You have a comparison from the SL, and your logic has this star true and both in pre and post condition, right?
Mhm,
Is that
yeah.
necessary, or you can use it as a frame rule, just drop it?
Okay, so this it is kind of necessary because you cannot specify just that X is not allocated, because if you do so, you cannot reach any state where X, because if you specify that X is deallocated, you are only talking about that part of the heap, and constraining the heap to be exactly that. And so you cannot reach a state where just X is deallocated. If X is deallocated, you end up with also having to specify that V points to something, and this something points to something else, because you only reach states of the heap where X is allocated and these things and these other things are true. Putting here this and separately true is a convenient way to not have to talk about the rest of the heap. If you want to get rid of that, you can, but you explicitly need to describe precisely the rest of the heap. And so in the post condition, we think it's more convenient to have this true. And once you have this true in the post condition, you get it also back in the precondition as a part of the inference process. I think you can remove it from the precondition. Like it still sounds if you remove it from the precondition, basically because when you do, let's say, this process, you refine at some point you refine the true to just the part of the that you're interested in. So here the true refines to y points to something and separately true. If you refine it to just true, to y points to something without this and separately true, you end up without the true in the precondition. But of course, this is not something you know a priori when you do the analysis. You find out only at the end when you can remove the true in the proof.
Okay, thank you. So I understand this is necessary in your logic. So I'm curious about if you try to design the practical tool, can I always assume there's some star true in both pre and post condition? And is that sufficient to solve most of questions we're facing in the bug findings?
Sorry, can you repeat the question?
So I just want to say, if you assume that it's a star true in both pre and post condition, is there sufficient for you to build a practical tool to verify all these test cases, for example, the ISL can verify?
No, we actually only have this example. So, but I don't really think it's a big issue to have this true here, because, for instance, if you want to frame something else, you can do, because true does not conflict with it.
Okay, great, thank you.
Yeah, we'll do one more.
Professor. So thank you so much, very nice talk. What I wanted to understand a little bit better was in this context of ISL and SIL, and you mentioned that this says a lot more than ISL because it says any state in the pre leads to somewhere in the post, right? And while in general I agree because of the interpretation of SIL, I think, or separation SIL, in this example, I'm a little confused because, okay, if you were to actually use the ISL axioms in the paper, first that existential quantification in the pre would go away. That doesn't need to be a dash, it could be an arbitrary value.
Look.
And once that's an arbitrary value, then the precondition is an exact assertion. So there's only one state in it. So even though that triple is saying everything in the post is reachable from something in the pre, there's something in the pre, there's only one thing in the pre, there's only one state that satisfies it.
Yeah.
So, and the whole argument that we're making in Unter and connecting it with Pulse was that if you don't arbitrarily weaken your pre using the rule of consequence, which Pulse never does, then really the kind of assertions that you get out of ISL are necessary to tell the developer what kind of problems you have.
Yeah, I mean, I agree, and no, I mean, this is indeed true. The point is that in general, here in the
But you said you only have one this example, and this is my point. I would like to see an example, but this is actually an issue. Like the kind of practical examples that we had in ISL or you have faced in Pulse so far, we haven't actually managed to pinpoint this theoretical limitation that exists potentially on paper.
Okay, yeah, so we'll have a look into this example if it exists.
Thank you.
Great. Let's thank the speaker one more time. And we have a break now, and we'll be back at 11.
Yeah, sure. No.
Okay, everyone, welcome back. In this session, we're going to have some more talks about program logics and program analysis techniques for correctness and incorrectness. So our first talk is by Andreas on unified compositional formal methods, and I'll hand it over to you now.
Yeah, great. Okay, so I'm going to talk about the things that we have been up to in Flippa's group lately, some of the people in Flippa's group. And maybe this something could be summarized as the unified compositional form methods, where unified means that we are interested in both over approximate verification and under approximate bound finding, and compositional. Test, hello? No? Better? It's apparently only this one. Okay, yeah, so unified or approximate verification and under approximate bound finding, those are the things that we're interested in at the same time. And compositional here meaning separation logic. More specifically, we have invented a unified compositional program logic. This was published last year, and then based on this work, we have also built a unified compositional symbolic execution tool/formalism. But since Filippa is going to talk about the Gillian stuff on Saturday, I'm going to focus on ESL here. So ESL being an abbreviation for exact separation logic. Let's start with an example use case to get some motivation. So this is you, and you're all dressed up because you have built a reusable library, for example, a linked list library. And these are some people, and you're happy because these people want to use your library. However, some of these people are interested in verification, so they want to use your library in verification, whereas some other people only do testing, etc. So you're no longer happy, because this means that to satisfy both of these groups, you would have to provide both separation logic and incorrectness separation logic specifications for your functions of your library. So 2 specs per function. Oh no, if only we had a unified program logic. So maybe I've also noticed the following. So if you kind of put separation logic and incorrectness separation logic next to each other, they look pretty similar. So for example, the heap mutation rule looks pretty similar to me. Well, allocation see some similarities there. Well, both of them have a frame rule, etc. So it might make sense to, in some sense, work in the intersection of these two logics, formally meaning something like this. So we define ESL triples to be valid if and only if the corresponding separation logic and incorrectness separation of the triples are valid. And this gives us the following proof system. So our rules are sound if they are sound in both these old proof systems. So in some sense this is a new logic, and in another sense it's barely a new logic because it looks pretty much identical to SL and ISL. So in terms of this use case, we can now be happy again, because instead of doing two proofs, we can do one proof in this unified logic. And if we do a quick comparison between these three logics, one could say something like this. So separation logic is a good fit for verification, because the kind of approximation you can do there doesn't allow you to drop execution paths, but it is not necessarily a good fit for bug finding, because you can drop information along execution paths. Whereas for incorrectness separation logic, you have the opposite situation. And ESL is a good fit for verification and bug finding, because there you're not allowed to drop anything. Okay, so after defining this logic, there are some questions to be answered. And I will focus on two questions here. Both of them being relevant for both currently existing and approximate separation logics. So ISL and ESL. So to do the kind of specs for functions we wanted to do, we had to think about the two following things. So the first problem, no one had fleshed out the rules for function calls in unapproximate separation logics, and therefore there were no soundness proof for this calls either. And also, no one had thought about abstraction in unapproximate separation logics. So let's talk about these two topics. So first, let's start with function calls in unapproximate separation logics. So this is, well, an example spec and some template function, some program arguments, some function arguments and some program variables, etc. And what is interesting here is that these two things, so the pre and the post, they talk about the external behavior of your function. Whereas when you're reasoning about this thing, the function body, then you will be reasoning about the internal behavior of your function. So a natural question is, what is the relationship between these two behaviors of the function? So in our approximate logics, these two behaviors kind of coincide, or they are so similar that we barely think about them. And why is that? Well, because the difference between these two behaviors are basically these program variables. And if you have, for example, or if you have the internal behavior, so in the sense that you have done a proof about the behavior of your function body, then it's very easy to derive the external behavior, because in our approximate logics, you can just throw away any kind of information you want. So just throw them away, you don't think about it that much. But in other approximate logics, it's a little more interesting, because there you're not free to throw away whatever information you want. So one way to think about it is that in our approximate in other approximate logics, you can only drop information when the information is also dropped in the program semantics. But this is exactly what would happen here if you call this function. So at function exit, you do drop information, loads information, in the sense that the program store that you use when you execute this function is just thrown away. So therefore, you can reflect this operation into the logic. And this is, well, a little verbose for now, so we can summarize it as this. So we capture this forgetting by a mechanism that we call internalization, which basically allow you to, well, throw away this information that is thrown away in the programming semantics. Whereas the function call rule, when you actually use the specs that you establish, is looking pretty much the same. You just have to be a little careful with the program variables here again to not lose information. But this is right. This kind of looks like the separation logic function call rule. Okay, so then there is this second topic, abstraction. So what do we mean by this? So this confused us maybe more than it should have initially, but after we realized or remembered that abstraction and approximation is not the same thing, it made some more sense to us. So this kind of function specification, where the list predicate here is just the normal inductively defined list predicate, meaning that we have a list in memory which is of length n, and the function is just a list length function. So this spec is valid in this exact separation logic. And why is this? So informally, we can look at the SL spec and ISL spec separately. So of course, the SL spec is valid. We have seen, well, everyone in here has seen this spec many times in over approximate logics. But it's also interesting that the under approximate spec is valid. And why is that? Well, formally we would have to do the proof, of course, but we can reason about this informally as well, because if we cannot find a state in our post that is not reachable, well, then this is a valid spec. And here it's quite easy to see that all of these states will be reachable, because if you take a model of the post, well, we will get some list, and the return will be the exact length of the list. And to reach this, we simply use this model of the post as our model of the pre, and then we get there. So in this case, it's quite easy to say that all of these are reachable. And maybe another way to informally think about this is that in some sense we didn't have a lot of information to begin with, so therefore we do not need to specify a lot of information in the post. So yeah, therefore we do not drop information here, so therefore this is a valid under approximate spec. And some specs look a little more interesting in under approximate logics and exact logics. So if you look at a spec where we add an element to the beginning of the list, then it looks a little messier than the spec you would expect in over approximate logics. And why is this? So it basically comes back to, again, that we are not allowed to drop information. And here, it all centers around this x here, x being the pointer into the list. And the messiness arises from our need to describe what happens to this x. And this is probably easier to see if we visualize it. So let's consider this example pre-state. So we have some example list containing 3 and 4, and then we have this x pointer into the list. And then the post state, if we add, for example, 7, will look something like this. But actually, not all of these post states, or not all of these lists that look like this will be reachable, because we had our pointer into the data structure, and this pointer will necessarily end up in the second position of the list. So therefore, we cannot just say that, well, we have a list starting with 7. We have to say that we have a list starting with 7, and also the second pointer of our list is our previous first pointer. Because if we don't include this information, we would over-approximate the reachable states. And to be able to say this, we need to expose all the pointers internally. So this is why this x's is here. So x here is the pointer into the list, the x's are the internal pointers, and vs is the contents of the list. So we still manage to capture, in some sense, the full behavior of the function, but here we have to expose more details than we would have to in over approximate logics. And another way to see this would be to think about what would happen if we didn't include this listed thing here. So the thing that is restricting where x will end up. Let's say that we actually use the function spec without listed. What will happen then in under approximate logics? So let's say that we have a list in memory, and then we, for example, copy this pointer into the list into another program variable. So now our state will look like this. And then we have to massage it a bit to fit our function call rule. We just have to take care of the program variable, as I mentioned before. And then we do the actual call. And if we didn't need to describe what happened to the pointer into the list and expose the pointers, then we would have something like this, where we end up in a state where we don't know anything about y. But this is bad because before the call, we knew that y is null because, well, x is not necessarily null if the list is empty. And this is exactly what listhead would say in this case. So if the listhead of the non-existing internal pointers would be there, then we would know that y is null. But so this is some of the things that we had to deal with to be able to actually use this logic for the kind of functions that we were interested in. But then this, I would say, is maybe the most common question people have after seeing this. So do we really want to, well, use a logic without approximation? So for example, our session share puts this worry like this. So, well, is it really practical, basically, to not have consequence forward or backwards? So we can go back to our initial use case and think about what does it mean to not have approximation here. So one way to think about it is that not having approximation is a consequence of the kind of specs that we're interested in rather than our program logic. So we are this person down here very happy because we have this unified logic and we want to serve these people that want to do both verification and testing. So in some sense, well, if we would over-approximate, then our specs cannot be used for testing, and if we under-approximate, they cannot be used for verification. So we don't have much choice here if you want to at least unify these two logics, being separation logic and incorrectness separation logic. Because if you want to actually capture the full behavior of our various functions of our library, then it wouldn't help if our logic could over and under approximate, because when we reason about these kind of functions that captures the full behavior of the function, well, let's say that our logic could, for example, drop execution paths, that is being an approximate logics. So if we, like in the middle of our proof, just drop some program paths, then, well, in the end we wouldn't be able to show that the actual full post here is reachable. And similarly for over approximate logics, if you just throw away some information, well, like if you throw away like the contents of the list, well, probably we cannot show that this post is true. But this is just the case for us as library developers. Let's say that we are not necessarily interested in exact specs. So let's say that we, for example, we are this person up here, so we just want to use the specs that have been proved about this library for verification. Well, then you can over approximate how much you want, because you can just use ESL and you just use our ESL specs in SL because they are compatible. And similarly, if you're interested in testing, well, use ISL and then we'll take the ESL specs from this library and then just derive the ISL specs because they are implied by ESL because ESL is a strong logic. However, if you're this person down here and you want to provide specs that are useful for both verification and testing, then, well, maybe ESL might be a reasonable logic for this. So, short summary of the paper, we introduced this ESL logic, and then we give rules and prove soundness of how to do reasoning about functions by formalizing this internalization mechanism. And then the paper also contains some more examples of doing abstraction in other approximate logics. So we provide some specs for example, single list library and some functions over balanced trees. Yes, that's it.
Okay, we have time for a few questions.
Thanks for the talk. I was wondering about the consequences of having no approximation when you're talking about loops, because obviously in an over-approximate setting you can have loop invariance, and in an under-approximate setting you can just consider like a finite unfolding, forget about other branches. But in this work, as I understand it, you can't forget about branches because it has to be an over-approximation as well. And so is it the case that the precondition has to ensure that you're only considering a finite, that the loop can only be unraveled a finite number of times?
Yeah, so the loop has to terminate, yes.
Okay.
And also so if you have some kind of something that could not terminate, for example, recursional loops.
But is it, regardless of termination for individual instances satisfying the precondition, is it the case that all instances of the precondition together must only enable a finite number of unfoldings? Because otherwise you couldn't talk about all paths without over-approximation.
Yes, the meaning of the triple is basically this. So, well, this is the total whole triple or total subpersonality triple. So it has the usual meaning. So for all states in here, it necessarily terminates in there. And this is the usual ISL triple. You can pick anything there that must be reachable from P. Yeah.
Sorry, so it is possible to capture all of the paths without over-approximation. For example, you have the proof of the list length that is fully general. So you can do it. The problem is that then what would happen is that you would really have to precisely describe your loop, which is just fine for list length, but is going to be less fine for the other ones. That's basically it.
You kind of have to include the termination condition in the
Yes,
postcondition
you will
as
get
well,
it, yes.
in order to ensure that it goes both ways.
Yes, in a sense, yes.
Okay.
You can take a look at the while rule. It should reveal.
Okay, thanks.
Thank you.
Yeah, we have one more question.
I was wondering what this sort of thing means for, maybe this is a general question about incorrectness logic, but it seems like you have to expose a lot of information in your specifications, and that seems to imply like a brittleness to changing the implementation of a library. Like, I'm imagining, your code works out fine, and then someone tweaks the implementation of list to be something slightly different, and then kind of everything breaks. What does that kind of mean for sort of modular program development or reasoning?
Yeah, for example, these kind of specs, in some sense, there's not a lot of abstraction going on here because you expose, well, basically everything, all the internal pointers, and you say exactly what happens to this pointer into the list, etc. But yeah, if you want to use incorrectness separation logic, you basically have to do this because you have to describe the full behavior here. So either you need to add some kind of mechanism to your language which allows you to do some kind of encapsulation, or you would need some other logic where you don't have these strong guarantees that you actually can reach everything. But yeah, it's an interesting question and something that I'm thinking about and working on right now, because I also want nicer specs than this, because I don't think these kind of specs are nice enough for actually using them. But it also very much depends on what your algorithm is. So in this case, it gets very ugly because something from the outside somehow ended up inside the data structure. But it seems to be some ways to address this.
Great. Let's thank the speaker again.
Yeah. Okay.
You're not getting the signal? Oh, wait, 1 second. We can fix that.
Okay, great. So our next talk is going to be about different kinds of errors, proving that programs do not terminate. So, you know, usually we would want programs to terminate, so if they don't terminate, that's a problem. And
Okay, cool.
Ready?
I think it works.
Okay,
Yeah.
great. So I'll
Thank you
turn
so
it
much.
over to Caroline.
Hi everyone, my name is Caroline, and I will be talking today about research that I did during an internship with Bloomberg, where I was supervised by Azalea Rath and Julian Van Eyck. For my background, I did a bachelor's degree in mathematics, and I'm right now studying in Amsterdam, so I come from the mathematics side. So the problems that we looked at was exactly as Noam said, termination and divergence. Of course, we would like all of our programs to terminate, but it's quite difficult to show that, and specifically if we actually do have divergent traces, how do we find those? So the approach that all of us probably know is the total logic, where we say, well, we have triples, and our post condition is a superset of what can happen. And all of our traces terminate. And this is really good if you do this analysis and it works for your program. It goes through, that's amazing, congratulations. You don't have divergence problems. But if it doesn't go through, then you're in a place where you don't know if there's actually divergent traces, or maybe because this is an over-approximating analysis, you actually over-approximated and have a false positive bug report. So the approach that we took to this was, well, we don't want to show that all executions terminate because most likely they don't. So instead we want to show that there exist executions that do not terminate. And this is really, this approach is really dual to total logic in the same way that incorrectness is a dual to our over-approximating logics, because we say, well, we don't want to show the absence of bugs in every case. We want to show that cases exist where those bugs do happen. So the way we do this is through under-approximation. Oh no, it's not. But because incorrectness logic is dual to our normal logics in the same way that our approach is dual to total logics, it makes sense to look at incorrectness logic and see if we can get somewhere. And you are all familiar with the incorrectness triples, I assume. They give us the existence of terminating traces. And they reason in a sort of backwards fashion. And by that I mean is you say, well, for every state in the post condition, there exists a state in the precondition such that there is a trace through executing C that gets us from pre to post. So by backwards, I mean you first quantify over the post, and then you quantify over the pre. This is working really well for a lot of applications. But the problem is if you think about divergence, you don't have a post state to quantify over. You want to say that from a pre-state, you can reach divergence. So you sort of need this different direction to get to. So what we do instead is backwards under approximation. We've heard Flavio talk about this before. They call it the sufficient logic. And this is also what was conceived as the Lisbon triple by Derek Dreyer and Peter Hearn. And this particular version on it is also based on the paper by Azalea Rath, Julian Van Eyck, and Peter Hearn, of which you can find a preprint online. So this triple says, for every state in the precondition, there exists an execution of C that leads to some state in the postcondition. So we say, we know about some program behavior and where it leads, but there's a lot of program behavior we don't really care about and we don't really need to characterize. So because we have this different direction that we first quantify over the pre-state and then go to the post, we can very naturally define a divergent version of the triple that looks like this, where you say, this triple holds if for every state satisfying the precondition, there exists an execution of C that diverges. And this is really cool, but of course the question is, what does it look like when we use it? So during my internship, I looked at different forms of divergence. We looked at while loops. We looked at recursive functions. But I want to talk about today about goto soups, because they're quite interesting because they are so unstructured and lead to a lot of chaos. So our setup is that we say a program is a partial finite functions from labels to commands, or you could also envision it as a bunch of blocks of code that are numbered. And goto commands allow us to jump between these bits of codes. And of course, as soon as we have that, we can jump in circles, and we can do that forever, and we have divergence, which is exactly the problem that we would like to take care of. If we execute goToL, you can see it in the logic rule on the right. It just means that we go to the program block of the same label and execute that block. Now the question is, what are the conditions under which this divergence appears? First of all, it's very straightforward that we have the necessary condition that we have to jump to the same label at least twice. If we don't, we can still have divergence, but then the root cause will not be goto. The root cause will be something else. So we jump to the same label twice, but the problem is we have structures such as assume, so we can change the control flow, and it's possible that even if there's a cyclicity, we go through that cyclicity a number of times, like 3, 4, 5, whatever, but at some point the program still terminates. So it's not enough to say that you jump to the same level twice, because we can still terminate. You need another condition, which is a sufficient condition, and that is that 2 of these jumps occur under the same assumption, and I will get into detail about what I mean by that. But the idea is that at some point we arrive in a place and we look back at the history of our execution, and we say, wait, we've been in the exact same place before. So we have this sort of cycle, and we can find this sort of divergence. So to look at an example, this is a very, very simple, very stupefied example, where you say you assume that some variable x is positive, you increment it, and then you go to 1, meaning you jump back to the beginning of the line. Now we would like to reason about the fact that go to 1 can diverge if you start with a positive value x. So you say x is positive, we execute go to 1. That means that we execute the program code saved at label 1. This is just a sequence, and we can go through it one by one. We assume it's positive, well, it's still positive, and if we increment the positive x, it is of course still positive. And now we're in the state where we say our assertion is x is positive, and we want to execute go to 1, but we look back into the history of what we've done before, and we've been in this exact place before. So that means we can just go back to the start and execute the same thing again, and we can do that again and again and again ad infinitum, leading to divergence. So this is all very fun, but of course now the question is, how can we actually formalize that in a logic, because we would like to reason about it, of course. The way that we do that is we introduce something we call a conditional triple. This triple is parameterized not only on the program, as all of triples are, but also on G. And G is a list of labels and assertions. And intuitively, G is the history of what we've seen before. So we say such a triple parameterized on G is valid under the assumptions that if G is a list of things that we've visited before, the triple PC infinity is a valid triple. So we say under the assumption that everything in G we've seen, that G is our history, we know that we have divergence. But of course, we would like to connect this to our normal triples, because if you just add on parameters and parameters, it can get very messy very fast. But the way we do that is quite simple, because if you choose G to be an empty list, you say the assumption is that everything in the empty list we've seen before, which holds vacuously true. So the conditional triple parameterized on the empty list is actually equivalent to our normal divergence triple. And now we need rules to reason about it. So what we would like to do is we start with an empty G, and we start executing. And upon every goto call, we have the label we call and the assertion we call. And we check if it's in our history. We check if it's in G. And in one case, if it is in G, if we say we've seen it before, we can say, oh, then we have divergence, right? Because we found our cyclicity. But of course, there's the second case as well, where the label and the assertion have not been recorded in our history before. So what we do is we say, well, it's not there, but we have to add it to our history because we go on now, right? And we want to remember that we have passed this point. So we append this to G and then continue executing, which is, well, the program code saved at label L because we just did a go to L jump. So to wrap that up, I would like to go through the example we've seen before, but this time we are going to do the proper proof. And the way I do this is I put in red, or it looks more like orange, things that we haven't proven yet, and things that we have proven or are trivial are going to appear in green. So we start with the go-to one, and well, the only rule that we can apply is the go-to step rule, because this is an empty list, so our label and our assertion cannot be in the list. So we say, well, it's not in the list, amazing. So we add it to the list. We now have a list of length 1, which has the label 1 and our assertion that x is positive. And we are now executing the program code saved at label 1. This is the sequence, so we go through them. The first 2 bits are quite simple. I have excluded the rules for assume and increment that actually do it because the slides are only so big. But I'm sure you agree with me that these 2 triples in green hold. And now we're in a place where, again, we're still in the assertion x is positive. It's a very simplified example, indeed. And we, again, want to execute go to 1. But now our list has that label we tried to jump to. And it has that assertion that we're currently in. So this is the point where we say, wait, we've been here before. We don't have to go on. We have found our cycle because we could just do the same thing again and again. So we can apply our go-to-rec rule, and we can say we've done. We've just proven that this program has divergent traces. Thank you so much for listening. Please ask questions. Yeah, thank you.
Hey, nice talk, thank you. After the increment on x, you have x greater than 1, that's 0, right?
That is, yes. I mean, if you want to stay exact, yes, but this is not an exact logic, right? Because we have the, because we are in backward over approximation. So what our triples mean is, oh, 1 second. So we say we're starting in the precondition. There exists an execution C that leads to the postcondition, but if we have an execution that leads to the postcondition x is greater 1, we also have traces that lead to the postcondition x is greater 0, right? Because this is as Flavia talked about, we have the forward consequence rule in this logic, so that's why it still holds.
And I have a second question,
yes.
if you allow me. So you keep the list of locations and predicates, but because you're liberally applying consequence rules sometimes, you could change the predicates in some minute ways.
Yes.
Like your condition is in, it's not like it's implied by one of them in so.
Exactly, yeah, that's a very good catch, that's true. So instead of saying, instead of saying here that it has to be that assertion, we can say, well, it's included in some assertion. Or you could apply the rule of consequence before, like you choose that. I kept this representation because I didn't want to muddle the rules even more because I, tried to show the simplest version and then explain it. But you're correct, yeah, that works just as good.
My question is, why go to? Why not something like while or any recursion, anything?
Yes. So while, I mean, we can handle while with these go-to rules, but we also have a rule to handle while because while is a lot easier, right? It's a lot more structured. So go-to is a more interesting case because it's more chaotic. So you have to make more effort to take care of things. We also worked on functions, and in fact, this logic is completely functionally compositional. We can prove terminating and non-terminating specifications. And our functions have local variables. So there's the added difficulty that Andreas talked about in the previous talk, that we sort of have to forget variables and bring them back once we've returned the function and so on. So we've done all of that. I just chose to concentrate on GoTo because I think that's the most fun case.
So if you go back to slide 24, your definition of your triples.
Oh, wait. I didn't even realize I had slide numbers.
There's
until
no
now.
24. Yeah.
Yes.
Could you redefine the triple as P implies the weakest liberal precondition of false?
I believe so.
Where for WLP you take a maximizing.
Yes, I believe so. This is what Flavio talked about, right?
No, he was under approximating WP, where WP maximizes.
Wait, sorry, can you restate your question?
So you say P implies WLP of 0.
Weakest precondition of false.
Weakest liberal precondition of false.
What is that? Can you give me the definition of that?
Yeah, so that's all states that either terminate in the post condition or not at all.
All states that either terminate in the post condition.
But by maximize, you mean you're taking some sort of angelic?
Yeah. For non-determinism, you take angelic.
I'm not sure I can answer the question because I only know half of the words you used.
Yeah, we'll discuss. Later.
Yeah, let's discuss that later. But I'm very interested in that. But I think Azalea has something to say about that.
I don't think so, because we're not saying this is definitely not terminating at all. We're saying it's possible for some traces not to terminate at all. There you're saying they all terminate or they don't terminate at all.
Yeah, but I'm taking WLP of false, so there's no final state to reach.
Saying there's definitely a trace that doesn't.
Yeah.
Yes, that's true. Yes.
Yes.
That is what we're saying.
No, it's not.
No.
WLP of false is those states where you terminate on every or you fail to terminate on every execution path. That's what so.
Oh, okay.
But it's related if you have angelic instead of non-determinism. Yeah. It's just like the weakest possible precondition, I think, is WP for angelic. You seem to know that.
There's some doubt there.
This is all related to angelic conditions.
Completely different question. So you phrased your logic in terms of programs with gotos in them.
Yes.
If you take a while program, you can compile it down to a goto program. So you should be able to derive similar rules for while programs. Have you tried that?
Yeah, we have rules for while, and they are very, very simple. So that's why I didn't include them, because if I did, then people would probably be like, well, seen that before. Tell us something new. But yeah, exactly. We have the rules, and they are a lot simpler than goto.
Do you have some completeness result? Like if there is a diverging trace, your logic, you have some derivation in your logic that can find it?
I don't think so yet.
We have two versions of this.
I think you need to speak into the mic.
We have two versions of this logic. One where we only focus on while loops for now. For that we have completeness. This extension that Carolina's worked on handles functional recursion and also gotos. We don't know yet if it's complete, as in we haven't done the work yet, and we don't have an intuition for it.
Hi, thanks for the talk. So if I look at the specifications that you have here, and I'm imagining a program with two while loops, the first one terminates, the second one doesn't terminate. I guess I have to prove for the first while loop, the first triple, right?
Yeah.
And here you have, it says an execution of C that terminates. So does it mean that for the first while loop, I need to prove that it terminates before I can then go to the second while loop to prove that it does not terminate?
You have to prove that it has terminating traces, yes, in the way that the logic is defined. So I think you picked up on the fact that this logic, if you don't look at the divergence, it is total in a way. Because we say, starting from pre, there exists an execution that terminates, and we're not saying there exists an execution that either diverges or terminates. So the answer would be yes. You could, in theory, change the logic a bit, and interestingly, I don't think that it would change a lot about the rules if you were to try to define it as a partial version. The only thing that would change is that functions are easier to deal with because you don't need to prove that functions terminate.
Thank you.
And one more note, because someone asked about functions earlier. I think it was you? Yeah. We can do functions, and it's all like, I mean, it's interesting and it works. But really, we didn't introduce any new ideas for the functions. All of the ideas came from exact separation logic, which is what Andreas talked about earlier. So we just took that proof system and changed it a bit so that it works for our logic.
So
Thank you so much for amazing talk. I have a bit of a naive question, but I was wondering, how do you run into any decidability problems when you're doing something like this, especially once you mentioned some sort of completeness for being able to find the diverging execution?
I'm not sure about that, because again, like, I'm from the mathematical side. I like come up with funny rules and then I prove soundness, and then I'm very happy because I finished the proof, but I don't actually know if it's useful in real life. So I cannot actually answer that question. I'm sorry.
Anyway, thank you very much.
Is there one more? Okay, let's thank the speaker again.
Oh, sorry, I was going to run off.
Okay, great. So our next talk is about modeling incorrect programs in the real world with Daphne. So we'll just wait 1 second while the presenter is getting hooked up.
The usual. Sorry.
Great. Yeah. So here we have James, and I'll give it over to you.
Yeah, the usual advice is never to start with an apology, but I'm going to ignore the usual advice because it seems that every single other talk in this entire incorrectness workshop is about, well, incorrectness logic or variants of it, and that's not really what I'm talking about. Although I think it's related, and I'm pleased to have the opportunity to talk about it because hopefully people will be able to tell me A, what I'm doing wrong, and also B, how it is in fact related to other work on incorrectness. This is stuff that I've been doing with a bunch of people, this is on there, particularly Sophia and Julian Mackay for a while now. At least 5 years ago there was this obscure talk about swapsies on the internet. And effectively what these things are trying to do is look at how we can specify and then reason about partial programs or programs in what we call the open world. And what we mean there is, well, this kind of thing. This actually happened to me this morning. That's my phone busily saying, you know, should I actually trust the computer that I'm plugged into? Should we trust computers? I'm very tempted to mention the police and what is it? The Police and Crime Evidence Act, 1984. We'll get there. Which, of course, requires legally in this country that you have to trust the computer. The computer is your friend. The computer is correct by presumption, by legal presumption under the common law. This is why there was a statement by the British Computer Society last week suggesting that that's probably something that could change, and why I'm taking a couple of minutes out of my talk to randomly talk about other stuff, which is, I think, if you happen to be engaged in formal methods or formal specification work, and I don't know why, I've trusted the computer. Now may in fact be an extremely good time to talk to the next government about the kind of legal standards and about the kind of academic research that would support, well, you know, trying to avoid national scandals involving lots of people killing themselves. Right, anyway, so, as Ward Cunningham used to say, I am the bank account. What do we mean by this open world stuff? Well, the environment we're working in, we'll say an open world, you could think about it as JavaScript. You could think about it as pretty much any situation where the code that we write has to connect to programs that come from somebody else whom, well, we don't really trust. Perhaps they're the post office, perhaps it's somebody else, who knows. So the system as a whole contains of both our code and then third-party code. Perhaps we're interested in future modifications. So in some sense, the third party might be ourselves projected into the future, as odd as that may seem. We may have invariants or requirements for our design that are necessary, say, to maintain security, and what we're saying is we don't want future modifications to the system to breach those requirements, or at least not to breach them without knowing what the hell is actually going on. So this is where we will often talk about things like trust, which I guess pretty much in the sense, do you trust what the post office computer is telling you? Are you willing your phone to trust the laptop it's plugged into? and something that I won't talk about in this talk, but is kind of lurking in the background, which is the risk, which is the idea that when something is incorrect, and this I guess is one of the connections back to incorrectness logic, maybe, if something is incorrect and we go ahead and run it anyway, and this is why I'm going to be spending, unfortunately, the afternoon in the parallel workshop on object capabilities, can we quantify the damage that will happen? If we run some incorrect code, or we run code that we're not sure whether it's correct, what I'm going to be talking about in the rest of this talk is about how we can make our specifications in some sense, if not robust to those conditions, but at least aware of them. And then there's like this complementary area of work, which again, we're carrying on with, haven't got completely tried up yet, about what happens in the worst case. If in fact we trust something we perhaps shouldn't have trusted, how much we're going to lose. So again, comparing this stream of work, we could call it robustness, call it various things. Then again, the traditional spec is a closed world. We will assume that we have the entire program and that we can verify the entire program. Things like Bertrand-Meyer, I know I shouldn't mention that associated with POPL, designed by contract, where he says when you're writing code you never check your preconditions. That is an embodiment, that rule is a hard embodiment of this notion of a closed world. Because you can only not check your preconditions if your preconditions aren't part of the attack surface. If some kind of adversary code cannot get into the middle of your program and then call something, and if you're assuming you're only being called by people you trust, well, then if you are called by somebody who is untrustworthy and you don't check that the preconditions, you probably won't be able to maintain whatever guarantees you need. So the open world has larger attack surfaces. Whereas the traditional specifications are pre and post conditions. Typically, we will have pre and post condition specifications, but we will also add in temporal conditions. And again, there's a couple of papers at Uppsala and Phase, I think, over the last couple of years where we've been working on these ideas. Again, I think it's related to this distinction between sufficient conditions. If I've got some kind of logic specification which says you may run the login method if you have a username and a password for the system, we might be interested in a necessary condition which would say you only can log into the system if you possess a valid username and a password for that system. Okay? Now I won't wave the laptop around because it's plugged into the projector, but the laptops you have, all of those will meet that sufficient condition. If you type your username or whatever, or give it a fingerprint, you can log in. But in fact, they will generally not meet that necessary condition that you have to have a username and a password to be able to log in. And is this actually because of a bug? Peter's grinning. The answer is no, because there's a .rhosts file, which pretty much says I'm willing to trust these other computers, and if I've got a valid login on that computer, I want my computer to accept it as a valid login for my system. And that perhaps is an example, again, of where you could say, if we had written this somehow had written this necessary condition down, saying, look, we really want these people to have a username and a password for this damn thing to log in, then presumably in some future world that Sophia and I and people in this room and everyone else are building, we want to get to the point where if you try to add in SSH with that hole in it, it would actually come back and say, I'm sorry, you put this in, you have broken this systemic, non-functional, whatever word you want to use, holistic, necessary condition that you have to be able to do that. Often what we'll find is that whereas traditional specifications really make individual functions explicit, often what we hear is we're going to make the emergent behavior explicit. That is, what the system as a whole does rather than just the particular individual functions, whereas existing specifications, that emergent behavior is implicit. If you've got either all the code or you've got specifications of all the code, you can work with them to derive perhaps the necessary conditions. Well, you can work with them to derive the necessary conditions, but they are not made explicit. We'll make them explicit. And in this talk, The kind of condition or emergent condition I'm going to be talking about is this notion of trust. You know, would you trust this computer? Would you trust this computer? Which is unfortunately, yeah, Imperial Computers Limited, anybody? You heard of them? You know why I haven't heard of them? Because in the late 1990s they fucked up a government contract called Horizon and then renamed themselves as Fujitsu? Do you watch television? Oh God, you're all millennials. You don't watch television, do you? Look, you should... I don't want to say this because it's probably not true, but doing something equivalent in New Zealand a few years ago did work for me. Watch the ITV program on the post office. I mean, you should do that as in your professional responsibility as a software engineer anyway. But I can bet that there will be grants that will be funded that will say, oh, remember the post office thing? We're going to try and do something to stop that happening again. So anyway, I'm using this picture because if you go to Fujitsu.com today, you can still get a sales brochure for the Horizon system, of which this is part. And you know, again, the reason I'm using this is not just to the whole Horizon thing. In fact, this isn't part of the main Horizon problems aren't what I'm really talking about. But just to make the point that if that's the center of Horizon, there are other systems, particularly other banking systems in here, with which it has to interoperate. These things are third-party systems, and the question for the rest of my talk is basically how do you make those dependencies explicit in your specifications? So, some worrying many years ago, before the pandemic, Sophia and I came up with specifications that look like this. Don't ask me to explain that because Sophia wrote it and I just copied and pasted it into the slide. Plus the paper was repeatedly rejected because we sent it to POPL. No, in fact it was rejected from all sorts of places. If you want to know about being rejected from POPL, I do strongly recommend the panel at last year's POPL that is available on YouTube, where many esteemed panelists go through and explain their favorite papers that they know were rejected from POPL and why it was the right thing for such significant papers to be rejected. Anyway, sorry, I really shouldn't do this. They're never going to invite me to keynote, are they? Okay. So, the point about this is that this is part of a specification. And this is actually the reason why it got rejected, because in the version that we've done so far, there is a circularity here, because what this is saying is in the specification we want to have, you know, a base level construct that says, does this object obey that specification? Now, it looks pretty much like, does this object have this particular type? And in a system where you did have a bunch of behavioral types that everything was explicit, that's kind of what it could be. But then if you think about what it means to be an open system, that's really what you can't have. Because if all the types and all the behaviors on all the types of your systems are all completely guaranteed, then from our perspective we say you've got a closed system because you've trusted everything, you've checked everything, that's all fine. That's great. If you're in that world, that's fine. If you're not in that world, and I'll resist making the political analogies even more explicit, then you have this question about how can you reason with that. And when I put that slide up, basically what this says is when it comes down to it, we have sort of a classical, or we had a classical Hoare logic, and again, the latest versions of this are in a paper that came to, I guess it's the year before last now, and we basically started encoding everything into Coq, and then haven't yet got anywhere near the point where we can really tackle this problem of trust and risk, which is where the brief bit that I am doing, or have been doing, I'll talk about, which is the guy, sorry Peter, the guy with the best hair in the business, Ruston. He's got a logo for Daphne, but every time I see this guy, I think, that's Daphne, isn't it? Really, it's Daphne, it's Ruston. It's like you're having a conversation with him. So, how many people, I don't know, if you don't know Daphne, that's fine. You should spend your time on Coq anyway, because you won't get papers into POPL if you really just work in Daphne. You've got to do the Coq. Even Lean is probably a bit, I don't know, sorry. Look, I come from the world of Uppsala and things, right. So basically this is a simple box interface which is effectively a reification of a variable, and the interesting thing there is that we are taking in integers but then we effectively have a constraint which says if you call set, trying to set it to something less than 0 or less than equal to 0, then we won't actually do the assignment. That is how you write an abstract specification in Daphne. You write it as a trait. And then, oh yeah, that's right. Important thing, well, a semi-important thing here, in which Daphne is sort of veering off towards the dependently typed languages. And there was a great paper by Jan Hughes and some other guy at the workshop on Sunday? Yeah. Sunday, which is trying to start pulling out those differences. Daphne has these things called ghost predicates, which you can think of as graded monads with a grade of 0, meaning these things are usable in the proof, but they are not usable in the actual running code that you might want to generate and run. Okay? Ghost variables. It's fairly standard. For those of you who speak only Agda, that's what it means. So in this case, there's a ghost predicate, and Matthew Parkinson is probably in the other room. Otherwise, I'd apologize for the fact that, well, in fact, that's a class invariant. And you know, what's the line? If class invariants had reached the end of the road, it would be necessary to reinvent them. Sorry. Right. So we have a class invariant that basically says, look, the value is greater than 0, and it's morning, it's evening, and we can do an implementation, which is not, you know, that's just the Daphne implementation of it. Okay, so far so good. What I've been playing around with is effectively doing this, which is a transformation of that, where, as well as that ghost predicate for the class invariant, I've got another ghost predicate, which I call a Bayes. And the idea is this is a ground level analog of that meta-theoretic Bayes that I had in the version of the specification language 5 years ago. It's rather ugly, but you know, it actually kind of is in Daphne. And the point here, it's an opaque ghost predicate. The ghost predicate means this only applies in specifications. You cannot test this at runtime, because if you could, that would be the analog of saying, well, I can actually go and ask, because basically a Bayes is whether this thing is trustworthy or not. By making it ghost, I can't actually go and ask that at runtime. And by making it opaque, that then means that Daphne will not look at the definition. So in as much in Daphne as I write code to this interface, and the other thing, the transformation I've done here basically is all of the pre and post conditions are conditional on a Bayes. So what this means is the code gets somewhat nastier, and I can write code like that. And this is basically exactly the same code as I had before, and the pre and post conditions just all have this Bayes in there, and up there's a ghost predicate, and we bind that to actual true. And I think actually we may have had to reveal it in the latest version of Daphne, but this lets you write, in this case, something that behaves the specification. It's an evening, it's morning, it's a new day. What we can also do is write stuff like this, which the important thing here is down here. That's really the only significant difference, which says we always do the assignment. We always do the assignment, okay? Now this verifies against that trait specification. How? Well, because every specification here is now dependent on this Bayes predicate, and in this bad version, the Bayes predicate is false. Would you ever want to write code like this? Well, the answer is no. Well, only to demonstrate at workshops. But the point is, this is effectively widening the standard interface to allow us to have both good and bad versions of the code, depending on whether or not these things are Bayes. And then, we can write code like there, where effectively, okay, we're making a good box, we're making an evil box, we're sending it to the same code. And down here we say, well, if the box obeys, then the box should be valid. And then we can call methods on it. And if we want to say this thing is going to have a value of 100, which is what it should have because of the specification, because when I wrote that trait specification, I said if you hand it a negative number, it ignores the assignment. You can write this and it will verify. But if you just say, look, this thing has the value of 100, it won't. It should all be kind of straightforward. but I think it's quite useful. And the important point here is that here we are effectively starting to accumulate explicitly the dependencies on the things that we don't trust. So that's basically it. There's a bunch of other stuff here, some of which I have done, some of which we are still working on. There are all kinds of interesting problems that we'll have to deal with. Yeah. And I've got a bit of time for questions for a change.
All right, do we have any questions?
Yeah, I'll take abuse or pointers to papers published in, 2011 that I should have read. Yeah.
Hi, thanks for your... It's on? Okay, very well. Thanks for the talk. I was wondering a bit about why you're doing this with the obeys clause. Is the point that you want to show that if a client or this outside world code is well behaved, then your code will get the proper result? But if it's evil, like you said, then you get an okay error? Is that a point?
Yes and no. So that's kind of half the point. So half the point is, if things go okay, it will go okay. But where we can get ourselves, as we've seen even in that simple example, we can have code that generates wrong results. What this puts in is it puts in that assumption. When in the earlier version it would have actually been the obeys clause in the specification language, and here the only thing we can prove is this, right? And this bit here is recording the fact that we are actually dependent on this external thing that we don't control. If we want to get rid of it, well, we could actually access the value, and then we can test it, and then we can test it dynamically. Daphne actually has features built in for doing that now, and there's work by Jonathan Aldrich and others on gradual verification, which is kind of also touching on this work, but I'm saying, look, that's in terms of sort of a methodology about how you might go about developing things. I'm saying, look, there are actual times when you just want to keep track of this information. If you do a lot of this, and if there are a lot of those systems, you will get a whole lot of these obeys clauses hanging around as preconditions, effectively tracking the assumptions underneath your specification. That's horrible, but at least it's in your face. And you've got the option of writing code that actually does a dynamic check if you decide you don't want to trust these things for some reason. So. But yeah, I mean, there's I think there are various examples, and typically it turns out that this is quite nice for cases where if both parties in a transaction are trustworthy, it'll all go through. If one party is trustworthy and one party isn't, depending on the implementation, you can often detect that, and then the thing won't go through. But if both participants are lying through their teeth, I'm tempted to say this is, of course, the anarcho-syndicalist assumption underlying most of the work on bitcoins and other digital currencies, but I wasn't going to make those kind of political comments. In fact, then you can't actually really give any guarantees, because you end up with, well, the guy on the left obeys if the guy on the left obeys this and the guy on the right obeys this, then the right things will happen, and if not, who knows what will happen? Because basically you get the situation where each participant in the interaction is just having to carry on whether or not it makes any sense on the off chance that they'll be given something of value. So, yeah.
Thanks.
Okay, we can do one more quick question if someone has.
You might have a quick question, but whether you get a quick answer or not is
That's true.
I'm happy to unplug my laptop.
All right, let's thank the speaker again.
Thank you.
Okay, great. So the last talk in this session is a different perspective on all this correctness and incorrectness stuff, comparing these logics based on Kleene algebra. And our speaker is Lena. We'll just give 1 second for the microphone.
Let's go.
All right, great.
Okay.
Take it away.
Thanks for the introduction. I present some stuff that Benjamin Kaminsky and I have been working on. So we have already talked about several program logics today, whole logic, incorrectness logic, of course, but there are many, many more, such as sufficient incorrectness logic in the talk of this morning. And the objective of this talk now is to build a taxonomy of program logics from the perspective of predicate transformers and Kleene algebra with top-end tests. So yeah, we will try to build a picture such that we can fit all of these logics in. And yeah, let's start with discussing some program logics. Consider this very simple depiction of a program here with a set of final states highlighted, and then the weakest precondition is just the set of states from which computation always terminates, and always terminates in the states satisfying the postcondition, so these orange states here. And we then say that a triple, oh yeah, so these are in this example states 1, 2, and 3. And we say that a triple is valid for total correctness if all of the states in the precondition are contained in the weakest pre of the postcondition. Now this weakest precondition calculus was introduced by Dijkstra, and there are many variants of this today. But one variant that was already introduced by Dijkstra is the weakest liberal precondition transformer. And this includes the states from which computation diverges. So for this example, this is state 5, which is then also included in the weakest liberal pre. And we then say that a triple is valid for partial correctness if all of the states in the precondition are contained in the weakest liberal pre. Yeah, so now we want to reason about non-deterministic programs. So here you can see that from state 4 we can either terminate in state 3 or 4. And as a consequence, we have to choose how to deal with non-determinism. And there are two main methods. One is we resolve non-determinism in our favor. This is called angelic. And we can also, if we don't resolve in our favor, it's called demonic. And this behavior can be included in the transformers, giving us two variants of each. So we now have four different transformers to look at. And what exactly is the difference between them? Well, the demonic weakest pre transformer requires all possible paths of the execution to terminate in the postcondition. So for this example, these are still states 1, 2, and 3. But the angelic weakest pre transformer says, okay, it's sufficient if there exists a path to the postcondition. So here you can see there is a path from state 4 to the postcondition. So state 4 is actually now included. And then the angelic weakest liberal pre additionally includes the states from which computation diverges. So here's state 5 again. Or in this example, actually, all initial states are included in the angelic weakest liberal pre. And the demonic weakest liberal pre again removes state 4 from the precondition. So yeah, you can also see that there is an order between these sets. So the demonic weakest pre is the smallest set, and the angelic weakest liberal pre is the largest one. Now, to keep things a bit more simple, we will for now focus on these two variants. So we will assume that the weakest precondition or non-determinism in the weakest precondition transformer is resolved angelically, and in the weakest liberal pre it's resolved demonically. And this gives us now two triples, one for total correctness, and now this is actually, since we're using the angelic variant here and not the demonic, this is actually equivalent to what was earlier called Lisbon logic or sufficient incorrectness logic. And yeah, we also have a triple for partial correctness, but here we're using the demonic resolution, which is the standard choice. Okay, so we're gonna complete this picture in some sense, and for this we can first add two contrapositives of these triples here. So B is included in the angelic VP of C, WP, sorry, exactly if and only if the demonic weakest liberal pre of C is included, of the negation of C is included in the negation of B. Okay, so weakest pre and weakest liberal pre are both backwards transformers in the sense that we start with a set of final states and compute a set of initial states. But this can be also done the other way around. If we start with a set of initial states, here 1, 2, and 3, we can compute the strongest post condition, which contains the set of states reachable from these initial states. So in this example, these are states 1 and 2. And we then say that a triple is valid for incorrectness if the post condition is included in the strongest post of the precondition. And there's actually also a liberal variant of this calculus. And I recall that the difference between WP and WLP was the states from which computation diverges. And now dually, for the strongest post perspective, the liberal calculus includes those final states that are unreachable. So in this case, state 5 is included in this set of strongest liberal post. And we then say that a triple is valid for partial incorrectness if the post condition is included in the demonic or in the strongest liberal post. And this is actually equivalent to what Clouseau called necessary preconditions. Yeah, so a lot of renaming here. I'm sorry about that, but we'll resolve that. And we also have to decide what to do with non-determinism here. And as for WP, for now we will focus on the angelic variant of strongest post and the demonic variant of strongest liberal post. And these are this is like the standard choice of incorrectness, so the incorrectness logic that you're familiar with probably. Okay, so let's add these triples to our picture. So we now have here partial incorrectness and incorrectness, and these both also have a contrapositive. And now, interestingly, there's another connection here, namely a Galois connection between here, the partial correctness, and the contrapositive of partial incorrectness. So this leaves us with 3 blocks kind of here, the correctness, then the partial correctness and partial incorrectness, and incorrectness at the bottom. Now this is a very nice symmetric looking picture. So let's look at this from another perspective and see if we can kind of confirm these results. And well, the perspective we're going to choose is actually Kleene algebra with top-end tests. Now, Kleene algebra was originally developed as an equational characterization of regular expressions, and then extended to Kleene algebra with tests by Cozen to reason about programs, and then further extended to Kleene algebra with top-end tests by Zhang, de Amorim, and Gaboadi to actually for the purpose of reasoning about incorrectness. So this fits very nicely in here. Okay, I'm going to skip formal details and just give an intuition of how we can use Kleene algebraic equations to specify program properties. Yeah, so in general, a program in the Kleene algebra is seen as a program is modeled as an element of an algebra. And we'll focus on relational algebra, where we can think of a program as a relation over program states, and an initial state is related to a final state if there exists an execution from one to the other. So yeah, and we can compose programs, and in the relational setting, this is simply composition of relations or programs. So here's the program that we've seen before, and if we want to compose to this another program Q, which is just skip, so does nothing, so this is the identity relation, then we can compose this, and we get a new relation which contains exactly these highlighted pairs of states. Yeah, and tests are special elements of the algebra in that they are subsets of the identity relation, and they can be negated. So the relational representation of a property fulfilled by states 1, 2, and 3 is exactly this here, and we can also compose a test to an expression which then gives us this new relation. So we can see that effectively composing a test removes those states that fail to satisfy the property. And we can, of course, do the same for a property on final states, which gives us this relation. So this is actually only containing the pairs 2 and 2 and 3, 2, as these are, so to speak, the only paths through this picture. Now for incorrectness, for example, we are interested in comparing only the final states of such expressions. And this is not possible in clean algebra with tests, but what can we do? We can add a top element, which in the relational setting is just the universal relation, relating everything with everything. And if we compose this top element to the relation we had before, what we get is a new relation where all initial states are related to the final states of the previous relation. So, the point is that these all initial states are somewhat constant. So we can now compare the codomain of relations and also the domain. Okay, so let's see how we can actually express program properties. We can express partial correctness using this equation here, stating that a top BPC is equal to top BP. And this left-hand side of the equation selects all final states that are in C and can be reached from B. You can, you can see this in this picture here as well. The right-hand side here selects all final states that can be reached from B. So if these two relations are the same, then actually all executions that are started in B have to terminate in a state satisfying C, which is partial correctness. Okay, and we can give a very similar equation for incorrectness. Namely, here we compare again. This is the same. We can compare all final states that are in C and are reachable from B to now all final states that satisfy C. And if these two relations are the same, then for all states in C, there must exist a state in B from which C can be reached, which is exactly incorrectness. Okay, so what about the other properties that we've seen? It is kind of folklore knowledge that it's not possible to express demonic or the standard total correctness in clean algebra. But we found out that it's actually possible to express this angelic or Lisbon total correctness. This is something that we found out. And the equation for that is actually very similar to what we've seen before. Now we compare here all initial states that satisfy B and can terminate in C with all initial states satisfying B. So if these two relations are the same, then all states in B must have some execution to a state satisfying C, which was exactly this Lisbon or angelic total correctness. So let's summarize this. So we have seen that we can give cut equations or top cut equations for partial correctness and incorrectness. And now partial incorrectness, as we've seen before, is just the contrapositive to partial correctness. So we can also give an equation for that. And we have also seen that we can express Lisbon total correctness. Now you can see that all of these equations look syntactically somehow similar. And we wondered, there must be more equations fitting this pattern, right? And in fact, there are. For example, this one here and this one. And now the question is, what does this mean? What kind of properties are expressed by these two equations? And now, interestingly, the bottom one is an equation for angelic partial correctness. So this is one of the variants that we skipped before. but the top one is not angelic partial correctness, which might be like, yeah, what you would expect. So this is kind of weird, and everything up until now was very symmetric, and now, yeah, this is somehow asymmetric, and the reason seems to be this different resolution of non-determinism. So let's extend the picture that we've seen before to accommodate these different resolutions of non-determinism. Yeah, so this is the picture we have seen before, and I'm just going to remove the names and make some space for the other triples. And well, first I'm going to add what we've seen before, which are these demonic weakest pre and angelic weakest liberal pre transformers. And we've also seen before that there's an order between them. So the demonic weakest pre is the strictest transformer, so to speak, and then angelic WLP is the most lenient one. So we get an order of implication, which I'll add here too, to add more arrows to this picture. And we can do the same in this upper right part. And now if you look at this, yeah, you would kind of expect something similar to exist here, right? Something dual for this bottom half. And so this doesn't exist in literature, so but we were actually able to define a demonic strongest post and an angelic strongest liberal post transformer that fit into this picture, and that they in particular also fulfill these implications. And then, well, these added triples also have contrapositive relations, which is nice, the top half and also the bottom half. So this is now what we have, and I won't add anything more. But yeah, this is a lot. I mean, but that was kind of the point, to have like an overview and maybe a structure, see what structures are there and how we can relate them. But yeah, so let's look at the properties that we can express in top cut, because I've mentioned that there is some kind of asymmetry. And well, you can see there's a gap here. And yeah, these two can be expressed, but these can't. And yeah, the question is why, and we think we have an answer to that, which is just that we can analyze a program forwards and backwards, but it will always run forwards. So in some sense, it makes sense that there is a difference between this top backward analyzing side and the bottom half here. But yeah, there's another thing that is interesting, which is supposedly incorrectness and correctness are two sides of the same coin, right? So incorrectness is here. So we would expect the other side of the coin to be here, no? But total correctness is actually here. So yeah, what is this? And well, we can partly answer this. Here is actually these Lisbon triple or Lisbon total correctness that we were showing earlier. And well, this I don't really know what this is, but we're working on that. So the takeaway message is kind of, this picture is not as symmetric as it may look on the first glance. And yeah, we're working on figuring out where these asymmetries are coming from and how we can give like an intuitive explanation of how they relate. And we're also looking at like the effects of different assumptions on the program on this picture. So I think this was mentioned earlier as well. If the program, for example, always terminates, then the picture kind of collapses in some dimensions. And similarly, if we have a reversible program, for example, the dual thing happens for the bottom half. Yeah, and another thing that I think is interesting, all of the triples I mentioned here assume something either for all initial states or for all final states. But I think especially for reasoning about, or for proving the existence of a bug, it would also be interesting to have a logic that expresses something like there exists a single path from a state satisfying the precondition to a state satisfying the postcondition. Yeah, that's all I wanted to say. Thank you.
Okay. Yeah.
I mean, that's a fascinating talk. You know a lot that I wish I knew. This bit on existential triples is very interesting. I mean, I played with around with those, and
Mhm.
I mean, if I understand what they are, the difficulty I saw is they don't play well with sequential composition.
Yeah, yeah.
Right? And then I don't know what to do about that, but if you think, like, what's a transition subvariant, a subset of the transition relation? I mean, it's this kind of thing you're getting at, right? In order to prove incorrectness, we don't need to cover everything in the pre or everything in the post, right? As long as we get one of these things, we're good for proving incorrectness. But I guess what puzzles me is that it's hard to see how it works with program analysis. This is no criticism. I'm just
no. I don't have an answer to that. That's fine.
Maybe you'll answer that for us. But fascinating talk.
Yeah. It's just a thing that I think is interesting, but I don't really have a working proposal. Yeah.
Great. We have time for one more quick question.
You mentioned that there's this asymmetry between forwards and backwards analyses, and as part of your future work, I see the question when the program is reversible. But in this Kleene setting, and for non-deterministic programs in general, aren't they all sort of trivially reversible? Like I can take the reversal of a regular set of traces and it'd still be regular. So do you know why they're asymmetric?
Well, I think the problem is that if you have non-deterministic choices, say you have a program which is non-deterministically choosing between skip, so doing nothing, or diverging. This is a setting that cannot exist in the reverse way because there cannot be a final state that is unreachable and reachable. You always have, for all final states, you always have either unreachability, so no initial state can reach that state, or there are several ones or whatever. But in the other way around from an initial state, it can be that you either have or that you have non-termination, and termination. So I think this is like the main point why these Kleene algebra equations are not completely, or in fact, let me show you. This equation here is something like angelic partial correctness, but it says something like from all initial states, computation either always diverges or reaches, or there is a path to the post condition, which is not exactly angelic partial correctness because, but I think that's the reason. But
thanks. Okay, great. Let's thank the speaker again. And so we have the lunch break now, but please go upstairs and not downstairs.
sorry. Outcome logic, which is a monad parameterized logic that extend Hoare logic, and hyper Hoare logic, which further extend the outcome logic, but instantiated with the powers monad. And in particular, the two logics are pretty similar. They both lift the assertion language, going from predicates to hyper predicates. And by doing this, they show that they can subsume several existing program logics. In particular, they can also prove and disprove any triple within the same logic. And in this talk, I would like to argue that the predicate transformers deserve more attention, because as we are going to see, they subsume existing program logics, and also they have some advantages in the sense that they can find the best possible precondition or the best possible postcondition. So in particular, I would like to recall our previous work, which shows how we can define several logics by using predicate transformers. And for partial correctness, I have already said that we can just under-approximate the weakest liberal precondition. For angelic total correctness, also known as Lisbon logic or sufficient incorrectness logic, which means that every state in the precondition P has a path that goes into the postcondition Q after executing the program. And here we can just under-approximate the angelic weakest precondition calculus. Then we also defined partial incorrectness in our previous work, which is equivalent to finding necessary preconditions from Couzeau. And this means that every state in the postcondition Q is reachable only from states in the precondition P, if it is reachable at all. And this is equivalent to under-approximating the strongest liberal postcondition. And also incorrectness logic or reverse Hoare logic, which means that every state in the postcondition Q is reachable from the precondition P. This is equivalent to under-approximate the strongest postcondition. Okay, now I have finished with the introductory part, and I will show how we can lift the weakest precondition to our weakest hyper precondition calculus, which is a weakest pre-calculus for hyper Hoare logic. So the idea in the weakest precondition calculus is that they reason about predicates, and the predicates are just function from program states to either true or false, so to Boolean values. Instead, we will reason about hyper predicates, and hyper predicates map program states, map predicates to true or false, or maps states to either true or false. So for the classical weakest pre, the idea is that we plug in a postcondition, and in this case, we can take as example x less than 5, and we have a program. Here we increase x by 1, and we want to find a precondition, so a condition over initial states, such that all the states in this precondition after executing the program C will terminate with x less than 5. And clearly here the precondition is just x less than 4. So we can think of this weakest precondition as a forecaster, because if we plug in initial state sigma, what it does is to anticipate or predict the truth of the postcondition, but evaluated in the final state. So it anticipates the operational semantics of the program for a given initial state. For the weakest hyperpre, as I said, we reason about hyperpredicates. So instead of a postcondition, we have a hyper postcondition. And a hyper postcondition can be a condition over sets of states. For instance, here we have the sets of all sets of states such that there exists at least one state with x equal to 0. And we can think of this as a bug, for instance, or in general, this is also referred to main constant analysis in control flow graph analysis. And here we want to find again a hyper precondition, so a predicate over set of states. And clearly, I'm not showing all the computation, but this is basically given by the sets of all sets of states where there exists a state with x equal to -1. Because if we run the program, we will terminate with x equal to 0. And again, we can think of the weakest hyperpre as a forecaster, because here we plug in but a set of states instead of a single state. And what it does is to anticipate the truth of the hyper postcondition, but evaluated in the sets of reachable states after executing the program. And the set of reachable states is just given by the strongest postcondition. So here we are just anticipating the strongest postcondition. We can show that our weakest hyperpre subsume or is equivalent to hyperhorologic triples. And since hyperhorologic triple subsume several existing program logics, all the one that I have mentioned before, then we obtain for free that we also subsume these triples in our setting. And more interestingly, we can also show how to falsify this triple by means of predicate transform semantics. And this is also related to the existence triples that Lena has mentioned in the previous talk. So to falsify a partial correctness triple, we just need to find a state in the precondition P that has a path to the postcondition not Q. That is, has a path that goes outside of Q. So we can just intersect with the angelic weakest precondition. To falsify an angelic total correctness triple, or also a Lisbon logic triple, sorry, yeah. Sorry? To falsify a Lisbon logic triple, we just need to find a state in the precondition P that has no path to the postcondition Q. So we just intersect with the demonic weakest liberal precondition. Then for partial incorrectness, which I recall it means that every state in the postcondition Q is reachable only from the precondition P. To falsify this, we just need to find a state from outside of P, such that this state here goes into Q. So we can just intersect with the strongest postcondition. And to falsify an incorrectness logic triple, which means that every state in Q is reachable from P, we just need to use the strongest liberal post, which finds all the states that are reachable only from outside of P, and we intersect with Q. So we ensure that there is a state in Q that is not reachable from P. And all of these triples can be expressed with our weakest hyperpre transformer, so with a single transformer. Now let me show how to lift the reasoning from predicates to quantitative reasoning. So for the quantitative weakest pre that already exists, the idea is that to use functions from program states to real values instead of Boolean values. And we will lift these to hyperquantities, which are functions from quantities to real values. So let me show how the quantitative weakest pre works. So we have a post quantity as opposed to a post condition over final states. And for instance, we might be interested in the value of the variable x. And here we have a probabilistic program that with probability a half, it increases x by 1, and with the same probability, it increases x by 2. And we want to find a pre-quantity that is able to tell us what will be the expected value of x, but after executing the program. So in this case, it is just x plus 1.5, because on average, we can think that we are increasing x by 1.5. So again, we can think of WP as a predictor. Here we plug in a single state, and we obtain the expected value of x, but in the final distribution. For the quantitative weakest hyperpre, we use hyperquantities. So here we have, for example, a hyperpost quantity over final distribution, probability distributions. And as an example, we might be interested in the value, in the expected value of x for any given distribution. And we want to find the hyperpre quantity, which in this case, it's very similar. It is just the expected value of x increased by 1.5. So we can think of the weakest hyperpre as a predictor, but here we plug in a probability distribution instead of a single state, and it anticipates the value of x, the expected value of x, but in the final distribution. And even though this seems very similar, there is a main difference, because here we are making it very explicit that we are computing the expected value instead of, in some sense, hard coding that in the calculus. And in particular, we can also choose different hyperquantities. For example, we can think about the variance for any given probability distribution, or any meaningful measure over probability distribution. Or we can think about the maximum hyperquantity or the minimum hyperquantity, which for a given probability distribution, what it does is to compute f in the support of the probability distribution and take the maximum or the minimum. As an example, if we have a program that after the termination of the program, it stores in a variable n the number of requests that we perform to a database, for example, then with hyper-Hoare logic, one might be able to prove this triple, which tells that for every initial set of state, the mean number of requests is bounded by 100. But the problem of this is that it might be false, because maybe for some initial state it is not true. So one might try to find the right precondition, which might be hard. Or also the bound might be loose. So in general, it would be a lot better if we can simply measure how many requests we perform. So with the weakest hyperpray, we can do that, because this expression here tells for any given initial distribution what's the expected number of requests, without the need to try to guess a bound. And now let me show also how we subsume some existing transformers. So to let me show how the angelic weakest prey works. So here we plug in a post quantity and an initial state. And what WP does is to predict the final states and then compute f over all these final states and then take the maximum. And we can clearly mimic this using our weakest hyperpray by using the maximum hyperquantity. So we make it very explicit that we are finding the maximum. And instead of plugging a single state, we plug a probability distribution. In this case, the direct delta probability distribution, which and basically WHP will compute the final distribution and take the maximum over the support of this distribution. And we can do it very similar for weakest liberal prey, which just takes the minimum instead of the maximum. And more formally, one can show that our previous transformers are just specific instantiation of our calculus. And also the existing weakest pre-expectation transformers can be seen as instantiation of our calculus. And yeah, as for the, let me recap what we have done. So we have proposed the weakest pre-calculus for hyper-Hoare logic, and we enable quantitative reasoning. And also we show how to reason about correctness and incorrectness using a single predicate transformer. And for future work, we plan to further investigate a forward variant of our transformer and to develop transformers for outcome logic. Thank you for the attention. Any question?
So we have plenty of time for questions. Patrick.
I see that you are an enthusiastic about predicate transformer. I am too. The problem with WP and WLP is that they exclude runtime errors, and which is a cause of incorrectness. So in a sense, you exclude at the beginning a number of possibilities that are interesting.
Yeah, I think we can try to model these kind of errors. Maybe adding some extra states to check if we reach one of these errors. So in our work we don't. We have a very simple semantics, but I think there can be extensions to model these kind of things.
Yeah, they can be extended, of course, but you should extend it, I would say.
Any more questions?
So the normal, like, non-hyper properties correspond to, like, if I write an assert in the programming language, then, you know, you run the program, it trips the assert. And so it can be connected to testing very easily. Do we want to write hyper properties in the programs, or is it, I understand the probabilistic case, but is it for meta theory, or do we want to actually write these things in a program?
So I think for non-probabilistic cases, I think it's mostly meta theory. But so my take is that if we study properties over hyperquantities, so hyperproperties, then we might be able to derive simple logics for other use cases. And one can show that, for instance, if we have linearity, we obtain the standard weakest pre-expectation or things like that. So yeah, it's meta theory, but I hope to get some real logic, some yeah.
Okay, you can set up. Any other questions for Limpeng? Going once? Please.
You have one weakest pre here. So Limpeng, you have one weakest pre here, and you're characterizing like loads of other predicate transformers.
Yeah.
I mean, is there only, going backwards, one meaningful predicate transformer for hyperproperties, or are there other ones that you just haven't studied?
I think for hyperhorologic, this is the only one, and I think this is also the liberal. This is also the liberal transformer because we have some properties. And yeah.
Okay.
So this is the only one.
This was just switched off.
Oh, okay.
Yeah. This now works.
Okay. Can you set up, Heike?
Yes.
So let's thank Limpeng again.
It's on.
Yeah, but it's
Our next speaker is Heike. She is setting up, and as you know, we've had some issues with the mic. They tell me it is now fixed, so keep your fingers crossed. Thank you.
We'll deal with this a little bit. Okay. Basically, just don't hit the off switch.
Mm-hmm. Okay, thanks, Zed. I will talk about the reachability logic for a weak memory model with promises, and this is a joint work with Lara and Bridges, and Bridges is sitting at the end of the room. And the full paper has appeared at FM 23. So I start with the summary. What will we see now? So what we wanted to achieve is a proof calculus which allows us to reason about reachability. So I prefer to say reachability, not incorrectness, because it's not necessarily a bug if you reach something. So reasoning about reachability of concurrent programs, and concurrent programs running on a weak memory model, and not an arbitrary one, but one which needs the concept of promises to describe its behavior. And we wanted this proof calculus to be sound and complete, as well as compositional. And by compositional, I don't mean a rely guarantee compositionality, but what I mean is that you are able to derive proof outlines for threads individually, and then have a way of checking whether these are interference-free. So this is what I mean by compositionality. And I will explain everything on examples, so we will see almost no formulas here. So this is a load buffering example. So this is one of the standard examples in weak memory models. We have a concurrent program with two threads. They have shared variables x and y, and local registers a and b. And T1 is first reading from y into a, and then writing 1 to x. And thread T2 is first reading x into b, and then writing to y again 1. And what we would have if we have a normal Hoare-like reasoning is that we would be able to prove this Hoare triple here. So if we start in a state in which x is 0 and y is 0, all the states that we end in satisfy this predicate. So if a is 1, then b has to be 0. Why is this the case? So if a is 1, then this statement 1 here has to take place after 4, and therefore after 3. And therefore, if you do the read of this b, it can only read here from the initial value. It's not possible to see this assignment here. Okay, this is what we would do with normal Hoare logic. And now we go to incorrectness logic. In incorrectness logic or in reachability logic, you should, for instance, be able to show that if you start in a state in which x is 0 and y is 0, you are able to reach, among others, this state in which a is 0 and b is 0, and x1 and y1. I will omit this for the rest here. Because you can initially do these two reads here, statement 1 and 3, and then you see a0 and b0. But not necessarily all states at the end have these values, but just it's possible to reach one of these states.
Okay, so far we have assumed sequential consistency. So when I explained these runs, I was assuming that a concurrent run is some interleaving of runs of threads. So every thread exactly follows its program order, and then you interleave it in one way or the other. And what we now want to do is we go to a weak memory model. Weak memory models describe behaviors of concurrent programs on multi-core architectures. And these behaviors often look like you don't follow program order anymore, but you do out-of-order executions. If you, for instance, look at this one, this load buffering example again, then there is a memory model in which you can see A is 1 and B is 1 at the end. So it's possible to reach a state in which both registers have the value 1. This looks a bit counterintuitive. And to explain this, these weak memory models use these kind of promises. So this is a concept to describe what's happening on the architecture. And this concept is saying that threads can first of all promise to do some store instructions and only later fulfill them. And the other threads can read from these promises even before they are fulfilled. And if we now look at our example here, what we see in the state, so this is here part of the state, is for instance such a memory sequence. So this is a sequence of entries. Initially, you just see x0 and y0 written by some arbitrary initialization for t0. And then you have possibilities of entering new entries here. You have for every thread a promise set, empty at the end, at the beginning, and you have registers both initialized to 0. And what could happen now in this program is that before execution actually starts, is that threads start to promise something. So we could have, first of all, thread T1 promise x to be 1, and this is then an entry in its promise set and an entry in the memory sequence. And then we could have T2 promise y to be 1, so this comes into the memory and into its promise set. And now we can start executing our program, reading from y and from x. And this read would take place from this sequence here. So when we have the first read here, we can see y to be 1 reading from this entry. And when thread T2 reads from x, it can see x to be 1 in this sequence. So this would be then after these two statements. And now we need to fulfill this, so we can't end with the promise set which contains some entries. So these promises need to be fulfilled, and this is easy in this case. So T1 is doing this assignment, then the promise set is empty, and then T2 is doing the assignment. Promise set is empty as well. Okay, so this is the kind of behavior that we see here. But of course, not everything is possible here. There are also some disallowed behaviors, and this is an example of a disallowed behavior. So here you have a thread T1 writing to the same variable twice, and T2 reading from the same variable twice. And it's not possible that at the end you have A is 2 and B is 1. So these two writes cannot be reordered, or we can't see the effect of such a reordering in the semantics. Right, this is now what we want to look at, and now we want to build a proof outline which allows us to deduce these kind of triples about reachability on this memory model. And what we aim at is, at the end, to have a conceptually similar technique to concurrency reasoning for SC. In concurrency reasoning for SC, you build these kind of proof outlines where you have your program, and in between you have assertions. And then you have to check local correctness. So for instance, when we have here P1, execute C1, then we need to reach P2. So this would be local correctness. And we have some kind of global correctness or non-interference, which tells us that assertions that here are in here are not invalidated by the other thread. So this is completely standard Wikigrees. And we would like to be able to have a similar kind of a technique which builds proof outlines individually, and then we have a way of checking non-interference. And the challenges for this are that now we don't have safety, but we have reachability, we have a weak memory model, and we want to retain this form of compositionality. And the idea is now to use a particular form of assertions, particular unusual form of assertions, I would say. These assertions record ordering of events in the form of event structures, more precisely flow event structures, and they are actually almost exactly the ones proposed by Winskell in 1988. And we have lots of events in these event structures, different sorts of events. But in particular, we have events reading from promises and events saying that we now fulfill a promise. And now we look at our example to see how this works. This is the example with the disallowed behavior. So we should not be able to now construct a proof outline which guarantees us this state to be reachable, which is interference-free. So the aim is now to build a proof outline which looks like we could show this, and then at the end show they don't match these local proof outlines. So if we want to see A is 2 and B is 1, then thread T2 has to read from a promise that X is 2 and then from a promise that X is 1. So we start here with an event structure which just contains such an initialization event describing that we now have two writes, X0 and Y0. And now building this one here, we add an event saying I read from this promise of T1, I just guess, it might be T1 who fulfills this, X to be 2. And these two are ordered here because this is an event on X and this initialization is also an event on X. And then we do the same for the second read. Again, we just assume there is a promise that we can read from of X to be 1, again with the flow relation here. And now looking at T1, so this is a locally correct proof outline for T2. And if we now look at T1, we see kind of the dual case, but this is now doing the fulfills. So we start with initialization event and then have this fulfill here of T1 X to be 1, and then yet another one for X to be 2. Again, they are all ordered because they are all on the same variable. So, two locally correct proof outlines. Now, why don't they show that this is possible? So for the combination, we now do a parallel composition of event structures. And this parallel composition is synchronizing reads with fulfills. So every read has to find a partner in the other event structure. And they synchronize, so this is kind of a pairing construction, which then inherits all of the flows of these two event structures. So if we do this combination, we see we have this pair here. So we have the pair initialization. This is just ini. And we have these pairs for X1 and for X2. And if we inherit all the flows, we see that we get this cycle. And this cycle is telling us we have an interference here. OK, what about load buffering? Load buffering should now be an interference-free event structure at the end. Again, we start with T2. We assume that we can read from X being 1, and then we do our fulfill, or our own fulfill Y to be 1. And in this case, these two events will not be ordered because they are two different variables. OK, and T1 looks kind of similar. Here we have the fulfill or the read from a promise that we would like to see. And here we have our own fulfill. And if we now again do this synchronization of these two event structures, we see there is no cycle, and therefore this is a valid proof outline which shows us that this outcome is actually possible. Do I have time for yet another example? Okay. Now we have an example with a fence. Again, T1 is the writer, but to do two different variables, an x and y. And in between, we now have a fence. And on this side, we have the reader of first y and then x. And this is not possible. We can't see a is 1 and b is 0 at the end because of this fence in between here. And in the proof outlines, we can actually see this in the following way. This is now a bit different what we see here. So first of all, here, again, we assume we can read from the promise of y to be 1. And now, for the second one, if this is what we aim at, b is 0, we need to read from initialization. So there's no need to add a new read here into our event structures. But what we need, and this is kind of the only non-standard edge in this event structure, what we need to say is in between this promise here and the initialization in memory, there can't be another entry for x. So this is kind of forbidding something in the memories which are described by this event structure. So in memory, no entry for x in between e and e prime, so both of these events will be mapped onto entries in memory. Okay, so this is our proof outline for T2. For T1, we would fulfill x to be 1, and then we have the fence. The fence is an extra event here, which needs no synchronization partner in the parallel composition. And then we have another fulfill of y to be 1. And these are now ordered because you need to order everything with respect to fences. So when you have a fence, all the events after and all the events for are related in this, have to be in this flow relation. And when we now do another parallel composition, we see no cycles. So maybe first of all, what we see is this fulfill here has no partner. We fulfill something, no one reads from it. We don't care, so this is just a star here. And this one does have a partner. And it looks like everything is cycle-free. But what this arrow, this orange arrow, is now telling us, there should not be an entry to x in memory in between this here, the entry for this fulfill, and the initialization. But this one is exactly telling us there has to be an entry for x. So we call this memory inconsistent. So this would be another case of interference of these two proof outlines. Okay, then how does our proof rule at the end look like for parallel composition? So we are making proofs of this kind. We're starting with an event structure just with the initialization event and have something E here at the end. And this is possible if we have local proof outlines for every component Ci, from ini to ei, and all the E's are synchronizable, so every read really finds a partner, a fulfill that it can read from, and we are able to construct an interference-free event structure, which is the parallel composition of all these EIs at the end. So this is the way what I mean by compositionality. You can produce these individual proof outlines and then have a way of checking interference freedom and combine them. This proof calculus is sound and complete with respect to this reachability, and the technique is compositional in the sense that I just said, and basically that's it. What do we have? A proof calculus for reasoning about reachability of concurrent programs on this weak memory model with promises, and this calculus is sound and complete and compositional.
Questions? Thank you.
Hi, thank you very much for the talk. Could you please tell me about the underlying model? What are the restrictions there?
The weak memory model?
Yeah.
Yeah, so it's we started out with actually using ARM v8, but then made some simplifications so that it becomes tractable, because this is a really very complicated model. the main difference, I think, is that they have a semantics for where you have views for registers, and these views for registers can go back in time, whereas our views for registers can just go forward.
You mean promising arm? Or
the operation semantics.
Operational one?
Yeah.
Yeah. Not declarative. Okay. Do you like support the full like C++ like interface, or it's some restriction?
So it's not for C++. So it's not release acquire.
So you do not have release acquire accesses as well?
No.
Or?
No.
Okay. Thank you very much.
I was very confused by your use of event structures. So, what I remember, like an event structure is basically a set of events with a causality relation that should be a cyclic and a conflict relation.
Yeah.
And in your case, you have cycles, and I haven't seen conflicts, so I'm completely confused.
Yeah. So actually, conflicts. And so when you do this, parallel composition, you typically, or you could have, for such a read, more than one fulfill as a partner. So you build more than one combination of fulfills and reads, and they will then all be in conflict. So when you do the parallel composition, you will have conflicts. And in principle, everything that you start with here is acyclic, local proof outlines, these event structures. But when you do the parallel composition, you might have cycles, and then...
So you don't get an structure.
You don't get...
The object that you get is not an structure, if you have cycles.
It's a flow event structure. I think in a flow event structure you can have cycles, but then you don't have configurations which are random. Yeah.
Okay. I have two questions, excuse me. The easiest one is I have not understood when the promise is not fulfilled, what happens?
Yeah, but when the promise is not fulfilled, this is not a valid state to be reached. So if you would here at the end only have a...
It must be fulfilled.
Yeah, it must be fulfilled, yeah.
And the other one was in a wiki you need auxiliary variables, and Lamport showed that the program points are enough, and I wonder if you need them because of your sequences, maybe you don't need them, or...
For completeness, you mean?
When you have the sequence of events, do you still need auxiliary variables or not?
For achieving completeness, you mean?
For completeness.
Yeah. No, you don't need to, because I think it's because it's reachability. And so if you want to show that a particular state is reachable, with this proof calculus, then you know exactly what kind of execution leads to this state, and then you can really just build the event structures on the threads which follow this execution. So this is not so complicated.
I believe you.
Any other? Steve. This is the last question.
Thank you.
There it is.
Can I ask a question about the difference between validity and provability? I think you seem to be showing that you have examples where you say there isn't a proof using this methodology, and therefore the thing is invalid. But what you're actually showing is it's not provable using this methodology.
Yeah.
In principle, it could be still valid.
Yeah, these disallowed examples were just there for illustrating that we are really not able to show this with this. Of course, it's not really proving it, that it's not possible, but it was just to see how this interference works. Yeah.
Okay, let's thank Heike again. He was asking for Right, our next speaker who's setting up, almost there, is Julian Wang, and towards temporal adversarial logic.
Okay, where can I put it? Okay. Be careful for it to be on. Like if you don't see it green, then yeah. And Sorry. A little more. I'm sorry. Okay. Can I put it here?
Yeah, anywhere else.
You know what? You just try to put it yourself because I'm not doing it right. Yeah, that should be fine. Okay. Try to put it yourself.
Test.
Yeah, just put it this side. Try now.
Okay. Good.
Just trying to move it. Okay.
Yeah, let it go. Hello, can you hear me? Yeah. Good. Hello, my name is Julia Van Egg. I'm with Bloomberg and Imperial College London, and we'll talk about a work in progress that is about trying to bring the temporal reasoning to under-approximate logic. So why would we want to do that? First of all, temporal logic has been massively popular in the last 40 years for model checking and other techniques to verify programs. And so we're not going to reinvent anything of that. However, there is a reason why we may want to do more with temporal logic is because in the last few years, timing bugs and timing attacks have been on the rise. And not only in cryptographic code, but also in general purpose code. For example, if you start mixing untrusted data in a browser, for example, you may be able to infer properties of the trusted data based on your untrusted data, say they contain in the same containers. So there are a number of code patterns and classes of vulnerabilities that have been on the rise. And it's legitimately why we're asking ourselves whether we could actually use some of the temporal reasoning within the incorrectness framework. So that's why we're doing that. A little more concretely, many of you will be probably familiar with the model logics. So of course you have LTL, linear temporal logic, CTL, TLA, folks like Manap, Nueli, Lampert, and many people after them who actually worked on those logics for quite a while. However, if I put my developer's hat for a second, it's a little bit hard for me to really use those tools. Usually you need a verification engineer to go with you and actually annotate your code or do things on the side that is not intuitive for people who actually may benefit from those tools. And so one of the motivation of this work is really to be able to create a program logic, something that maps to the semantic of the programming language in your programs, and encode the timing information within the rules, within the triples, if you will. And so you may have assignments and then conditionals and while loops and so on. And even more particularly, we want to be able to do this in the under-approximate setting. So adopting incorrectness logic. For those of you who were in a talk at Orhans you've seen that already. But basically, adversarial logic is a mixture, a marriage, one could say, of incorrectness logic and the Dole-Fiao model, where you have an active attacker represented in the logic itself. So typically, you're talking about a parallel composition, P and A, where P is a program, and the target program, and A, the active adversary trying to sabotage you, trying to exploit your vulnerabilities. And it's not only for cryptographic protocols, it's also for regular code that in fact is vulnerable to some bug that could be at deeper level of interactions where you need multiple interactions with the target program to actually reach a vulnerable state. And in particular for the timing work, we care about relational properties. For those of you who may have noticed, in this relational adversarial logic paper, which is still being reviewed. In fact, I changed the perspective of adversarial logic from a saboteur model, which I call, to an arbiter model, where in fact your adversarial program here acts, instead of trying to actively sabotage you, is trying to actually execute several executions of your program or several different programs. and prove them not equivalent typically, or try to prove that certain execution of your programs are leaking some information, which is what we're going to talk about here. And to illustrate our purpose, here we're going to take this example, which is quite artificial, but really actually is sufficient to really understand what we're talking about. On the left-hand side, you have a program, a target program that contains an information disclosure bug. And on the right-hand side, you have an adversarial program trying to actually exploit this particular vulnerability. So let's look at the left column for a second. You have a couple of different random values stored in global variables sec1 and sec2. Say for secret 1, half of secret 1, first half of secret 1, first half of secret, the second half of secret. And then you have a while loop that reads a couple of values in variable x and y, and then it tries to see if the value of x that you just read from the channel S is actually different from the first part of the secret. If so, it returns a value, a status code, say 0. And then after that, it's going to try to check if the second part of the secret is equal to your second value read on the channel, say y. If y is different than the secret, the second half of the secret, then it's going to log a failure, and then return the same error code 0. Otherwise, it just returns error code 1, or status code 1. And on the right-hand side, what you try to do is to satisfy an adversarial contract, an adversarial assertion, where you want this particular assertion on line 7, assert that you want the return, the value that you read back is actually 1, meaning that you executed line 14 on the left-hand side. And so we have those symbolic variables, alpha 1 and alpha 2, and really the goal of the logic is to solve for those variables. What variable do I have to actually put in those values to exhibit the fact that, in fact, I can reduce the complexity of the attack. Here is in fact, 64 bits attack reduced to 2 times 32 bits. So it's way faster to actually attack the first part of the secret first and the second part of the secret later, knowing that you can differentiate between the 2 kinds of error at line 9 and line 12, because there is this log call, and that log call is very time consuming. Right? That's the intuition. And so what we're going to do at the logical level to encode this is we start from the incorrectness triple, where you have, for all states in Q, there's a state in P that is in the relation C, with a little epsilon can be either OK or error for the correct computations or the error computations. So we call epsilon a little tag. And in the adversarial triple, in adversarial logic, this tag is actually on the left-hand side as well as on the right-hand side. And the reason for this is because in adversarial logic, you can transitively reason about the knowledge of your adversary. On top of that, we add what you could think of as a little ghost state theory for tracking time. And what you do, in fact, is you parameterize a triple with a little time footprint, which is this big delta, and this big delta is dependent not only on the precondition P, the preset that you are executing your program in, but also the specific piece of code that you're executing, say C. And when it's actually ambiguous, we're just removing the C, we just write delta P. And similarly, the little epsilon is still OK, and or add, which is a generalization of this error tag for the adversarial computation. And so we're tracking, we're mapping that T1 to T2 by adding this footprint. Okay? And so how do you use this in practice? For example, if you want to exchange messages, you're reading or you're writing messages, you can use the Flory's axiom of assignment generalized to lists, where if you're reading a value in variable x from the channel S, right, you're starting with a precondition P, and x is whatever value you want, and S, the channel, actually contains a list of value L. Well, in the post condition, what you're going to have is that you're going to update the channel represented as a list, where you're going to append this triple, this epsilon T2, and X and in being like an input information that you're putting into your channel to track that this particular event was an input event. And you will map T2 equal T1 plus your little time footprint. When you're writing, it's quite similar. However, the triple that you append to your list is using out. meaning that it's tagging it as an output event. And as you see, it's monotonic, meaning that you don't have any interleaving semantic needed here, because you're just like appending data to both channels, and at the end you synchronize the reads and the writes event. And so, and on top of that, really important is that as part of those values that you push or that you put at the end of your list, you have the time footprint. So this particular value, the value of t is actually also put together on the channel. So t2 in that particular case. Okay, and similarly, you can very easily write summaries in your in this logic, where instead of actually going down the rabbit hole of analyzing the log function, you can just say, you know what, if I start my program at time tn, and then I execute log n, well, I can, for example, say that this is going to take 100 cycles. And so it's very easy. It's almost cheating, one would say, but it's just to show that it's a very practical way of thinking about how to analyze timing. Okay, and so I mentioned about the reads, about the writes, but how do you actually match that up after that? Let's look at this graphically. So the rule is a little bit complicated, and it's probably not in its final stage at this point. However, graphically, it's pretty clear what happens here. On the left-hand side, the two left columns, you have the process or the program that reads something into variable y. And on the second to left column, you have this write event, right, that writes the value of x. And the result of that, evaluating that, will actually produce two new executions. One where the y is replaced by the value that was in x, and then there is a residue, let's call it a execution for the right-hand side of the program that actually performed the write. But really, what's important to see here is that when you are, there is a the timeline of those events is actually being synchronized on the right time. Meaning that if you have a program, you're trying to attack a program that is doing a read, well, you can actually synchronize on the attacker timeline based on when you're going to write the value. And that's exactly why when you have those messages that first you send something, it gets read, and then something else is written back, and you read that, you can an adversary can actually synchronize the target program on its own timeline. That's really important here. So here you started with a process that went from P1 to Q1 on time T to T prime, but then when you actually compose this in parallel to a process that writes, then you will actually acquire the timeline nu prime of that process. You will not preserve the time that you executed with. And just similarly, when you take two executions, right, one is reading and writing, the other writing and reading, what happens is that those are not equivalent to, you can actually extract those, the differences of those time footprints. So I've had a number of discussions with people since I'm here about, oh, it's so complex to do relational analysis in the verification setting. You know, you have alternating predicate complexity, for all there exists, for all there exists, etc. It is very hard in the verification setting. However, we're not doing verification here. We're extracting behavior. So that's much easier. All right, and on top of that, I was interested in finding out whether there is some kind of structure to these timing interactions. And so I started to draw those boxes where you have a bunch of states, right, at say 3 different states at time footprint T1, say, and then you have a number of execution paths that go through. And those execution paths, actually, you see that you can go from the set of state at time T1 from the set of state at time T2 by actually using this time relation, let's call it now, epsilon 1. And similarly, you can go from those states at time T2 to time T3 with this epsilon 2, meaning that if you start composing those epsilons, in fact, you can go from time T1 to time T3, etc., etc. So where I'm going at with this is that it seems like there is some nicely formed algebraic structure to this, in the sense that you can exhibit the special elements of that algebra. You have say you have an identity, you have a 0 element, you have what we would say the common elements, E of the other unitarian element, where you go from T to T plus 1, and then you can actually iterate over that. You can go from T to T plus V times N if you have a number of repetition in a loop, for example. So it appears like there is more research necessary to really ensure that, but it appears like it's possible to actually map that to an algebra. And to conclude, there's a lot more work to get done to actually get from a, let's say, a temporal logic for verification to a temporal program logic where you track those time footprint, and particularly in the relational case where you can attack things like constant time programming bugs, where if you're able to actually characterize those execution based on their time footprint and their timelines, based on some specific message passing, I guess, semantic, you could extract some of those under approximation that hopefully we'll be able to find real bugs down the road. Before we get to an implementation, however, we need to think of it in terms of like instruction level semantic. There has been a lot of work, not a lot, but a little bit. I know like Hernan Ponce de Leon, for example, a couple of years ago came up with a logic to analyze side channel attacks at Auckland. However, here we under approximate. And if we're able to actually implement this at an instruction level, I think we'll be in a good spot to be able to start finding bugs, timing bugs. Thank you very much.
Patrick.
It's just a funny remark. The trick in temporal logic by Neuilly and Clark and so on is to forget about time. In the formula, you speak of the time without ever mentioning the time. And then in your logic, you only speak on the time. So there is some incompatibility here.
That's right.
Could you do it without the time? That is just replacing time by their formula or sequence of events or things like that.
I think you could probably map it to dynamic logic of RL using RL's modalities possibly. But however, one of the goals here was really to be able to map to the semantic of the programming language instead of staying at in this abstract model level of descriptions. And so in a very utilitarian, practical interest, if you will. So point taken, thank you for telling me that. And I think there's definitely way more work to actually do to get to a spot where we're happy with it.
Yeah, thanks for the talk. So one comment going on what Patrick said, there is actually time-temporal logic that you may be interested in, but they are more complicated. Also in the same line, you take as an example constant time, but constant time is precisely not about timing actually, it's more about dependence from the secret usually. So probably it's a bit a complicated way to make constant time. Maybe you should look at things like constant resource, which are more about timing itself than...
Right, so here I mentioned constant time, but really what the bug is you branching on a secret value, right? If you start branching on a secret value, that's when those potential breaks of constant time programming actually happen, or the leaks can happen. So I think you're referring also to like RT-CTL or RT-LTL, things like that, right?
No, actually, well, we can take it
sure.
offline if you...
Thank you.
Thank you for the talk. So I think I missed the basic intuition about this footprint time, so this delta thing, right?
Mm-hmm.
Is it, tell me if I'm correct or not, so I have the feeling it's a function that takes a command and a precondition and gives me a number. But how can, so if I set P to true, I have the feeling that it means I need to know for any state in which it started, basically how long it's going to take, which might mean it's constant time. Or said differently, I don't understand, for example, how your if rule could look like. Does that make sense?
The way I think about it is that the rules themselves, in fact, they are independent of that delta map, right? So say you were trying to map the time it takes for instructions to execute or statements to execute based on your pre-state and that particular instruction itself. Of course, in the real life, you need to model things like caching and etc.
Maybe so here P is a precondition, right?
Right.
So if a really simple example would be C is if X equals 0, log something, else skip, right? And my P is true. What would be the timing of that? Because in one branch, depending on the value of X, I would say it takes 100 cycles. In the other one, maybe 1. So you mean here I just choose which branch I take and then I... But if it's a... maybe I should pass better.
Well, no, I mean, just following up on that, is it a partial function? So it's like it may only sometimes be defined?
The delta?
Because if P isn't specific enough, then maybe delta is just not defined.
Right. So the way I think about it is that, in fact, the rules are parametric to that delta, meaning that they're not depending on it. And so if you provide a delta on a side, which I have, right, either you actually can provide a static delta, which I don't recommend, or you can actually infer that delta based on, for example, a runtime execution, right? So based on a real concrete execution, you can say, oh, this is a delta we're talking about, and then you don't think about it. You just...
So one last question, and can our next speaker begin to set up, please? I can't see where you are.
Thank you. I have a question about the bug finding part. So I have read your paper about adversarial execution, and my question is, you need to have the adversarial program, right?
Mm-hmm.
And so I have maybe a little trouble in understanding, but if I want to find a bug and I have to have the program, maybe this thing, I mean, it's useful to actually check that the program that I have already written, the adversarial program, that is.
100%. So thank you for saying that. In fact, if you were at Ohrenfest, you would have actually seen the work we're doing with program synthesis to be able to do this without having to provide the adversarial program. So we're basically starting from this vulnerable program, and then in that talk using by abduction and program synthesis, we're able to basically come to a point where we're generating the adversarial program.
Then I'll have to look into that then. Thank you very much.
Thank you very much.
Take your mic. Good. That's a very deep pocket.
Right. Our next speaker is Tobias Niesen on finding counterexamples to for all there exist hyperproperties.
Maybe it's better to...
And then coffee.
Okay. Okay, that should be fine. Try
Thank
speaking.
you. Hey. Seems to work.
And if you feel like it's not working, just check that it's there.
Okay,
and
thank
just turn
you.
it on.
Okay, hey everyone, my name is Tobias, and yeah, this is probably going to be apparently one of the very few talks that have pretty much nothing to do with incorrectness logic or any of these similar derived logics. So yeah, me and Georg, we are working on a kind of practical way of actually finding counterexamples when certain hyperproperties don't hold. So let's talk very briefly about what my understanding of incorrectness is, because that is a much broader sense than just incorrectness logic. So for us, what we think of incorrectness, at least recently in our research, is whenever we approximate a system and we try to do an under-approximation, and then we find something in this approximation that is not allowed by the specification, then we prove incorrectness, right? That's exactly what incorrectness logic does. That's what most of the talks today have been about. It's just a very general way of looking at this problem. So instead of over-approximating things and then trying to prove correctness, what this entire workshop is about is kind of under-approximating and then proving incorrectness, right? So we are looking at a particular class of hyperproperties which have significant relevance in practice, but which are unfortunately challenging in this area. So very briefly, what hyperproperties are in a very intuitive sense is it's properties that you can't prove or disprove by only looking at single execution traces of any system, whether that's hardware or software, infinitely many states or not. If you only look at one trace, you cannot prove or disprove these properties. That's a very informal definition, but it really depends on the logic that you use. So one very simple example here is what we call observational determinism, which essentially just says a system is observationally deterministic if for every pair of execution traces, if the inputs are the same, the outputs must be the same. Note that this is very different from a system actually being deterministic or not. We don't care if the system internally behaves deterministically or not. We only care about what we see from the outside. That is quite the significant difference, because if we looked at the internals and it behaved non-deterministically, we could decide that using a single trace only. But here we actually need pairs of traces of the same system to decide that. And yeah, so we can quantify over trace variables, which is much more powerful than only quantifying over the value of program variables or so. And in many cases, these properties, when we only have universal quantifiers, we can reduce that quite simply, or, well, depending on how efficient we want to make it, in a quite complicated way, to the verification of single trace properties. So as long as we don't have any quantifier alternation or so, that works quite well. And many under-approximate methods work as well. For example, bounded model checking, which is inherently under-approximate, it only finds bugs. It never proves, well, there are certain cases when it can prove that no bugs exist if you add certain assertions to the formulas. But in general, it's more convenient for finding bugs than for proving correctness. Now, things get much, much worse if we had quantifier alternation, as usual in any kind of higher order logic. So, for example, refinement, API refinement, is also sometimes called the correctness of implementation, says that if you have two different programs, P and Q, and you want to see if P refines Q, then you ask, if I execute P and it gives me, for some input, some output, does the original program Q have some execution? Does there exist some trace for the other program Q that would have given me the same result? So, for example, if you draw a number if you draw a random integer, it does not refine drawing randomly from the set of natural numbers, because the integers are a superset of the natural numbers. But the other way around, if you only draw from natural numbers, it's a refinement of drawing from integers. So yeah, unsurprisingly, verifying these properties is much more challenging. And what we kind of want to do instead, because most of the approaches to verifying these properties, if they work at all, if the property doesn't hold, and let's be honest, we have this workshop because most software has bugs. In most cases, the property that we are trying to verify does not hold. And most existing approaches in this area, if verification fails, they just tell you that. They either don't terminate or they tell you, well, I couldn't prove the property, good luck. And what we want to do instead is if the property doesn't hold, we want to give the user a specific counterexample explaining why it doesn't hold. And the existing approaches to verification of these can roughly be categorized in these 4 categories, where, for one, we have strategy-based approaches. These are usually based on game theory, where for the universal traces, you have players, and for the existential traces, you have players. And the players representing the existential traces have to try to make moves to counteract whatever evil action the universal traces are trying to do. And if there's a winning strategy for the existential traces, then the property holds. This is inherently incomplete because the existential players cannot see the future of the universal players. So there's a way using prophecy variables to make this complete, but then it really, really doesn't scale anymore. It effectively becomes useless. Then there are automata-based approaches, which are great. They are very convenient, but they simply do not work for infinite state systems. They are strictly limited to finite state systems. And since our primary application domain is supposed to be software, we kind of have to be able to argue about it. We have to be able to reason about infinite state systems. Then, of course, what most of this workshop has been about is hostile logics, and there are a few relational hostile logics that can reason about these properties and then can do verification. But those that do verification usually run into the usual problems with loop invariance, for example. So the state-of-the-art tool, there are ORHLE, whatever the acronym stands for. The paper doesn't actually say. It requires every loop to be annotated with a loop invariant. So automation is really challenging in most of these hostile logics. And there are some under-approximating relational hostile logics. But yeah, as far as I'm aware, nobody has actually implemented them in any way that works in practice. And then lastly, of course, you can always reduce to QBF, but that again doesn't work for infinite state systems because then you're constrained to a finite number of Boolean variables. And yeah, completeness also, of course, as with bounded model checking, is not guaranteed. So instead, what we want to, just for reference for anyone watching the recording, this is what the table was based on, so please read all of these if you don't trust me. So logics are complicated, and especially for software, we want to be able to deal with infinitely many states, we want to deal with variables over infinite domains, and we want to deal with asynchronous behavior. So this logic O hyper-LTL, it extends hyper-LTL. It is from a 2022 paper by Finkbeiner and Beutner, software verification beyond case safety. And yeah, it's a great logic, but it makes things horribly complicated. It is very convenient for the user because it lifts a lot of complexity from the actual formula to the implementation of the solver. So essentially what it does to implement asynchronous behavior is it maps whatever observations you have in your program. You can define arbitrary observation points within your system, and then it simply projects those locations onto a new set of infinite traces. So your traces become shorter if you have fewer observation points than every single point on your trace. But yeah, it maps infinite traces with a potentially infinite, no, it has to be an infinite number of observation points onto a set of shorter traces that then simply consist of the observation points. So it kind of synchronizes your observations for you onto a shorter set of traces. And now, very, very briefly, I know most of you are familiar with this just because we use symbolic execution a lot. I just want to go very, very briefly over a very simple version of symbolic execution. So all it does is very stupid. It goes through all paths in your program, and then it checks if it's feasible using an SMT solver or set solver or whatever you want to use for the theory. And yeah, in this case, for example, only 3 out of 4 paths are feasible, and the symbolic execution engine would only explore those paths and would give up on the infeasible paths. So it scales quite well. There are multiple tools that implement it. KLEE, I don't know how it's supposed to be pronounced, works super well. But of course, it's all incorrectness based. It's all under approximate. It will never terminate if you have any unbounded loops or so. So works well in practice, but not in theory. So our approach is very similar. We essentially, I don't want to go into the details of the algorithm too much because it gets kind of tricky. But yeah, our approach is simply for the universally quantified traces, we use symbolic execution to pick traces, to pick paths. Traces would be too specific. Traces would already assign values to variables. We just care about paths at that point. Then we derive some constraints for the SMT solver from the path we have selected, essentially just all the conditions along that path that we get during symbolic execution. And then we use bounded model checking using an SMT solver, or if you really want to constrain yourself to finite state systems using a set solver, that solves a rather complicated query of a fixed structure. So one of the future goals is to optimize an SMT solver for this particular kind of query that we're giving it. And yeah, that will either give us a counterexample if that actually has if the bottom model checking instance holds, then we've actually found a counterexample because this, as you might notice, the eventually here is already the negation of the original property. So if that holds, then we found a counterexample. Otherwise, we need to refine our set of constraints to further limit the search that the SMT solver can do during this bounded model checking instance. And yeah, that part, refining C, is a very, very difficult problem that I'm not going to go into much. There's a lot of existing research on that. Essentially, you have to under-approximate the set of inputs that could lead to this spurious output. And yeah, that is, we've heard about weakest preconditions today, and it's a very difficult problem. But for some theories, for example, for linear integer arithmetic, it's decidable, and it actually terminates in that case. For other theories, not, so constrain yourselves to easy problems. And of course, when we do this, it sounds simple at first, but we do run into a bunch of problems. The first is that all of these temporal logics, like LTL, hyper-LTL, and O-hyper-LTL, they all assume you have infinite traces. They all assume, in the case of O-hyper-LTL, it's even worse. It assumes you have infinitely many observation points along your infinite traces. And of course, we can't have soundness when we reason using these logics if we only look at finite traces. And with symbolic execution and with bounded model checking, of course, we only ever get finite traces that we consider. So there are some approaches to this. There's from Armin Biere, there's an adaptation of LTL from 1999 that defines bounded semantics, but we cannot adapt that to the hypersetting at all. Then there's LTLF, which works surprisingly entirely differently than the bounded semantics for LTL that Biere defined. You can have global properties that hold even on finite traces, which is not true in any of the other logics here. And yeah, then there is another paper from 2021 where there's 4 reinterpretations of hyper-LTL. There's an optimistic semantic, there's a pessimistic semantic, there's a halting optimistic, and there's a halting pessimistic semantic defined in that paper. Unfortunately, all those still don't really work for our case because we want to do software that has asynchronous properties and also infinitely many states. So we want to have arbitrary predicates from our theory and our formulas, and we want to be able to synchronize asynchronous behavior. So for O-hyper-LTL, as I said already, we have infinitely many observation points that the logic assumes, which makes it difficult to redefine these semantics properly. And we also have the big problem of asynchronous termination. We had a talk earlier today about finding out if something is not going to terminate. And sometimes you want that, but often you also want your algorithm to terminate. For example, RHLE, one of the state-of-the-art Hoare logics for relational properties, it assumes that your program always terminates in one output state, and yeah, it proves properties about that. On the other hand, HyperLTR was designed for yeah, infinite traces that never terminate. And our goal is kind of to support both. We want to have a tool that can handle terminating and non-terminating programs with different behaviors. So yeah, this was one of the problems we faced, properly defining semantics so that our counterexamples would actually be sound. The second problem is what we call divergence. It happens quite quickly. If you look at this very simple example program, there's always an integer b such that there is a longer trace to reach the observation point. If you try to apply bounded model checking here and you're drawing random natural numbers, there's no bound here, right? It's let's say it's Python or horrible JavaScript big integers or so. There's no upper bound on the length of the trace here, even though there's just one observation. So we know it's always going to terminate, but bounded model checking is never going to find a bound that does that. You can try to apply acceleration, that's what we do, but yeah, for the basic algorithm, this is a horrible case. Third problem, and this one is actually rather rare. We only encounter this in theory. We haven't actually come across any benchmarks that would run into this. There are instances where there simply is no, and now this is a rather complicated way of looking at it, there's no finite set or finite traces that would prove that something doesn't hold here. Now, we can see, of course, this property doesn't hold because there's always an execution where eventually A equals B. But yeah, the bounded model checking, again, cannot prove this because B can be arbitrarily large. That means you need to look at arbitrarily many executions. So either you need an infinite set of finite traces, which we can't do using model checking, at least not in this way, because we need infinitely many different paths, not just traces, or we need one infinite trace, and we can't reason about that. Fourth problem, what actually is the counterexample to an existential quantifier? For the universal quantifier, it's easy. We give the user one concrete trace. But yeah, the other part for the existential quantifier, we need to kind of produce a certificate that it doesn't hold. And just giving the user the proof that the SMT solver gave us is kind of useless to the user, because the SMT formula that we give to the solver is insanely complex. It has little to do with the original input. So now we need to retranslate that proof to the original input semantic. And yeah, this is also work in progress. We don't have much here to show yet. But yeah, we can give you the trace, but the certificate is actually quite difficult to achieve. If you look at the opposite case, if you look at verifying for all exists properties, what people usually do is they require the synthesis of a witness function so that for every input, the witness function then gives you the existentially quantified variable that belongs to that trace. The problem with that is even in the finite state system, it's double exponential time hard. So yeah, in infinite state systems, it's just never going to work. Yeah, just very briefly, there are some interesting properties that require more than two quantifiers, most notably perhaps generalized non-interference, which is super important for security properties. I don't want to, for time reasons, I don't want to get into the details too much, but essentially you say for every two executions that share nothing, there is a third execution that shares the low security input with the first trace and the high security input with the second trace, and that produces an output that is indistinguishable from the first trace. If you're looking into probabilistic programming or so, you'll say that this is not a good specification at all, but if we're only looking at possible outcomes, then it's an accurate characterization. So for that, of course, we have our base case where we have one quantifier. If you remove the universal quantifiers, then it just degenerates into bounded model checking. Then the symbolic execution engine will just produce a single path and nothing else. If you remove all the existential quantifiers, it degenerates into symbolic execution. The bounded model checking becomes trivial. And yeah, if you have more than one of either, then our implementation does a product construction, which in the case of verification would be horrible because most verification algorithms fall apart once you do product construction, and that's what most of the research for all safety, for all case safety properties is about. But yeah, in our case, since we only do symbolic execution, bounded model checking, it worked quite well. And yeah, lastly, we took two existing sets of benchmarks from the literature. This is from the Finkbeiner and Beutner paper from 2022. And yeah, surprisingly, it works quite well. All of these algorithms, all of these input instances, I should say, the property holds. There are no counterexamples that our algorithm could find. So when I mark something as green here with a check mark, it just means that our algorithm never terminates because it never finds a counterexample. You can constrain how many observations it should do, and then it terminates after that many observations, but of course not with any definite conclusion. There are three instances that diverge. yeah, it's not really surprising. There are 3 cases where there's an infinite loop before an observation point, or an unbounded loop, I should say. And yeah, of course, in that case, our algorithm is not going to terminate. Still, surprisingly, it works in many cases, even though these are kind of trivial. There are no counterexamples. More interestingly, the set of benchmarks from the RHLE paper, 2022, I believe, these are more interesting. There are a bunch of examples here where we do produce counterexamples. Again, no certificate, but we kind of believe the SMT solver for now. And yeah, there's 2 cases that diverge. There's 5 cases that require division, which we haven't implemented yet because it makes the whole problem undecidable. The decision procedure doesn't terminate anymore. And yeah, 1 example that I haven't encoded yet because it's, I don't know how to fairly encode it because it's written in a way that is very complicated. But yeah, overall, the experimental results are quite good. And what we think, we kind of lifted the QBF approach to SMT, so to support infinite state systems, which is very cool. It also means that for some theories, of course, it's going to become undecidable very, very quickly. But to be fair, the whole problem, even for single trace, is undecidable. So yeah, and one advantage is that the incompleteness that we have here is quite, we can characterize it quite well. So we can define precisely for what input instances it will and for which it won't terminate. Modulo decision procedures. Yeah, thank you.
Thank you, Tobias.
Hi, thanks for the fantastic talk. Question, how deep can you enroll? So up to how many observation points can you enroll? Because your number of paths is growing exponentially, and very likely after 1, 2, 3 observation points, it's just intractable.
Yeah, it really depends. Sorry, this input, this language is horrible. It's not Lisp, it's just the best syntax highlighting I can get here. So this is an example here that branches exponentially. It's, yeah, again, don't pay too much attention to the actual syntax here. But both input programs here, 1A and 1B, have a while loop that counts up to 10, or one counts to 10, the other counts to 9. And, no, sorry, 1 to 11, 1 to... Oh, yeah. Okay, so the first is non-deterministic and only increases x in some cases, and the other always increases the counter I, but only increases x in some cases, and then, yeah, we formulate queries about that. So this is actually quite slow. It's only branching, it only has a single observation point, but for the actual queries it has to construct 2 to the power of 10 paths for each SMT query, and then it has to do another 2 to the power of 10 such SMT queries, and yeah. So I can show you it's, if I remove the output statement, the debug output, it's going to be a few seconds, but even now it should terminate quite soon. So yeah, it really depends on the complexity of the input. We have some where we do 20. So from the Beutner paper for the Hyper paper, there are some instances where we can do like 25 observation points because they don't do exponential branching. If you have a for loop, for example, you also have a linear. Now, if you don't have any branches within the loop, only exit conditions, it also stays linear, right? So yeah, it depends on how much time and memory you have.
One last question and then coffee.
So part of the success of the unary incorrectness is that you're in a way making the problem easier by changing a for all into an exist.
Mm-hmm.
Like you only have to traverse one path instead of many. And so in your case, you're taking a for all exists, and I guess you're sort of turning it into exist for all. So you have both quantifiers still, just in a different order. So did you find that that's in any way easier or harder, or it's like relatively similar?
Yes, so I think the main advantage is that using symbolic execution, you can guide the symbolic execution engine using heuristics towards interesting paths. I think that's one very big advantage, for example, compared to the QBF encoding, where you have to encode all the paths simultaneously. And also we do change it to an exists quantifier, but we do quantify over paths, not over traces anymore. So even if there are infinitely many traces, there's usually only a finite number of paths, at least of a certain length. For example, if you have variables of infinite domain, if you were to quantify over traces, you automatically, even if you have a single observation point in a finite length, the random sampling natural numbers example, for example, automatically gives you infinitely many traces, And quantifying over those is much more difficult than quantifying just over the paths and then letting the SMT solver figure out what variables to assign. So I think those 2 points are the major advantages here. I can't give you any performance numbers because, well, in most cases it doesn't terminate or there's no comparison to any other tool. But yeah, I hope it's still somewhat convincing.
Thank you. Thanks, Tobias, again. Before you all run for coffee, I have a public service announcement, and that is that there have been a number of interesting talks and have been requests for either slides or preprints or whatever material you have available. So could our speakers please, unless it's proprietary material and will get you into trouble with your employers, please upload your slides, your preprints, any material that you have to the POPL website. Thank you.
Sure. It's nothing. It's empty. Yeah.
Try?
Hello? Hello? Cool. Yeah, okay.
Okay. We still have a few stragglers, not to shame anyone. So, welcome to the final session of the Incorrectness workshop. Congratulations, you made it this far. Our next talk is by Jojo, and a great title, I love it, Type-Based Incorrectness Reasoning, or, this is the favorite part, well-typed programs must go wrong. Take it away.
Yeah. Okay. Hello, everyone. Welcome to my talk. Type-based incorrect reasoning, or we say the well-typed programs never go wrong. I'm Jojo, and this is joint work with Benjamin Delaware and my advisor, Suraj Jagannathan from Purdue University. So first I want to show you the big picture of the verification. In general, we have two frameworks to do verification, the program logic and types. So if we want to verify the safety property, we treat this logic or the types as an over approximation of the programs. For example, in the program logic for the imperative language, we have Hoare logic. And in the world of types, in the functional language, we use the refinement types. But if we shift from the safety verification into the completeness verification, and we also go from the over approximation to the under approximation, so Peter here introduced the incorrect logic. And recently, we introduced the coverage type in the world of the functional language and types as an analog to do the under approximation reasoning. So published in the PLDI last year. So let me tell you something about the coverage type. So the program we try to verify is actually the implementation of test input generator. Here is example. This is the NetGen. It's a natural number generator. It's implemented by the InGen integer generator by take its absolute value. And the property we want to verify is the coverage completeness. What we say the test generator must generate all test cases satisfy the given property. In the example above, we will require the NetGen must return all natural numbers non-deterministically. What happens if an implementation loses the coverage? So consider the following buggy program. It's a 10 divide x minus 10. X can be an arbitrary natural number that is the result of a natural number generator. And if we lose the coverage, it means that the test cases cannot cover a single case x equal to 11, x equal to 13, and that exactly the case can trigger the division by zero exception. So if you lose the coverage, it means that we can fail to find the bug regardless how many times we run the test, regardless how many test cases generated by the test generator. So the coverage completeness is quite important for the implementation of the test generators. And I will talk a little bit about this language we focus on the syntax semantics. So in general, it's a simple type lambda calculus, but with non-deterministic semantics. So a term here will reduce to multiple values instead of the single one. So the constants is a term, and 1 can reduce to a singleton value 1. And we also have non-deterministic choice, 1, O plus 2, can reduce to 1 and 2, non-deterministically. And the NetGen can reduce to all possible natural numbers. And the InGen can reduce to all possible integers. So what is the definition of the coverage type? So that's quite similar with the refinement type. Here is an example of the refinement type, which consists of 3 parts: self-reference, base type, and qualifier. So the example above, the base type is integer type, and the qualifier is y equal to 1 or y equal to 2, we here is a self-reference indicates the term self. And if a term E can have a refinement type, it means that for any value E can reduce to, that value can satisfy the qualifier phi. On the other hand, the coverage type is quite similar. We use a different bracket, use a different colors, the color blue to distinguish from the refinement type, and they have the same structure. The only difference is the interpretation of the qualifier different. So the meaning of the coverage type, if you look at it, you will find that the qualifier here is actually in the left-hand side of the implication instead of the right-hand side. So it means that any value satisfies the phi, the term must reduce to it. So the coverage, in some sense, implies a reachability. So I will give you several examples about the coverage type and refinement types. Here's the 4 refinement types and 4 coverage types. If we focus on the first term, the constant 1, then it can have all possible refinement type. Additionally, we'll have the coverage type v equal to 1. Because the term 1 can reduce to a singleton value 1 that covers the value v equal to 1. And for 1 O plus 2, it can have additionally besides can cover v equal to 1, but can also cover the v equal to 1 or v equal to 2. And for the NatGen, it can have 3 coverage types because it can cover more things. And for NatGen, it can actually have the top type. The top means that the NatGen can cover all possible natural numbers, integers. So the next interesting thing is subtyping. If we try to see the inclusion relation of these qualifiers, and we try to take a look at the subtyping between these coverage types, and you'll find they are contravariant. So look at the v equal to 1 and v equal to 1 or v equal to 2. That is 1 is included by that, and v greater than 0 in the top. And you see that is a contravariant. That is different from the standard refinement type system, which is a covariant from this inclusion relation between these qualifiers. So in some sense, we say the coverage type inverts the standard subtyping relation. And there's a very similar things happens in the Incorrectness logic paper about the symmetry rules, and it also inverts the standard Hoare logic. So after introduces the coverage type, and we compare the coverage and incorrectness verification. So when we try to do the incorrectness verification, try to prove a program is indeed buggy, it's actually try to prove a reachability. So we say the program must reach some state, satisfies a given property. Here's an example from the original Incorrectness logic paper. We say if we assume the x z equal to 11, and we execute this program, and we want to say there's a program state z equal to 42 is reachable. And our coverage type try to verify the coverage completeness. It means that test generator must generate all test cases, satisfy the given property. As we said before, the coverage can imply the reachability. So that is a very natural question we want to ask. Can we use coverage type to verify the incorrectness of the property of the program? The answer is yes, and that is the main topic of this talk. So the type-based incorrectness verification. And in the following slides, I will tell you how to do it, and that is quite simple. By just rewrite the program a little bit, and the coverage type can already handle it. So let's get started from the same example we showed that before. And the intuition of the type-based incorrectness verification is try to simulate the test procedure. So what it means about test procedure? So the first step, we try to rewrite this program from the imperative language to the functional language, because currently coverage type is designed for the functional language. So we say when the x is even and y is odd, we return 42. Otherwise, we directly return z. So that have the same meaning from the program on the left-hand side. And the second step is quite interesting. We add a random initialization procedure. That is consistent of the precondition z equal to 11. We say z equal to 11, and the x and y have no constraint. They can be arbitrary integer. So we simply say x and y are a result of some int gen. So in some sense, you can treat the random initialization procedure, generate different test cases non-deterministically, and we test the original program. So that's how I say I simulate the test procedure. So In another perspective, if you compose these two parts together and the self, it can be a large test generator. In that sense, we can also do the coverage type check. So what we do here is that we rewrite the post condition into the coverage type because here we don't care about it's a functional language, we don't care about the x and y. So the qualifier of the coverage type can only simply say the v equal to 42. That is the thing we're interested in. And if the coverage type check success, it means that the whole test generator can cover the value 42. In other way, we say the coverage implies irreducibility. It means that the program in left-hand side indeed reach the z equal to 42. So that is how we do the type-based incorrect verification by the coverage type. So the original incorrect logic paper additionally can track the correct and erroneous execution by the label OK and error. How can we do that in our coverage type? So take a look at another example. It's also from the original incorrect logic paper. And what we try to solve this problem, just use a product type to check both correct and erroneous execution. So like before, we also rewrite this program into the functional language, and we add a random initialization procedure. And additionally, we define the type of status can be OK or error. And that works like error monad. We say the function for full return not only an integer, but the product with status is indicate if that execution is OK or error. So if x is an even, it's just error. Otherwise, that will be non-deterministically return OK or error. So we also rewrite the post condition into a coverage type. So this label error or OK is directly rewrite into the part in our qualifier st, which means the status is equal to error or OK. So that is how we track the correct and erroneous execution like incorrect logic in coverage type. And the last part of things about the function type. Of course, this type we show here is the result type of the full. But what is the function type? Function type also has the parameter type. So what is the type of the parameters? Actually, there's two choices. The parameter can be over-approximated, can also be under-approximated. So what is here's example of the over-approximated type. And the meaning of this type means that all values satisfy the property phi2 that is in your result type must be returned by the function call for each input value satisfy the property phi1. Here is the for each. And if you use this under approximation parameter type, it's similar like the left-hand side, but we use different brackets to indicate that it's under approximation parameter. And the meaning of that, the two lines, the first two lines are the same. The difference is that we say that for some input value satisfies the property phi1. So the difference that one is for all, another exists. So in some sense, because the left-hand side is for all, the right-hand side exists, the over-approximation parameter type is also a subtype of it's more precise than the under-approximation type. But another direction doesn't hold. Actually, we need to make a trade-off between the precision of the specification. It's not to say we should always use over-approximation parameter types, or we should also use under-approximation parameter type. Here's an example. Consider the following program. We say the x can be arbitrary value, and we take the absolute value of the 10 to divide x minus absolute value of 13. And of course, when x is equal to 13, there's a division by 0 exception. So this program is buggy. And that is something we want to prove. The program is indeed buggy. So this incorrectness property can easily translate to the following coverage type. The parameter types are under-approximated. This means that it can be there exists some integer. So that is the top type. And the post condition says that is error. However, what is the type of the ABS? The ABS, if we take still treat as under approximation type, maybe we can say that v equal to 10 is a parameter type. It worked for the first application, but fell for the second because the 13 cannot cover the value 10. And we say if the v equal to 13, it fell in the first case. If we disjunct them together, they fell in both cases because the 10 cannot cover both 10 and 13. And if a conjunct of them, so that is simply a button type, itself is wrong. So actually, we don't want the under approximation type here. We want the over approximation type. It's actually very precisely describe what happens if you feed me a 10, I return you 10. If you feed me a 13, I return 13. So in that sense, both under approximation type and over approximation type we needed. So our future work to try to get the benefit of both of them. Okay, so here's a summary. If people want to do the type-based correctness verification, we can use this refinement types, where we treat the types as over approximation of the program, and we can say well-type program never go wrong. On the other hand, if we do the type-based incorrectness verification, we can use a coverage type, and we treat the type as the under approximation, and we can say the well-type program must go wrong. So maybe we can design the type system to unify both of them. We can both over approximation and under approximation. That is a thing we'll try to explore. Okay, thank you.
Thank you so much. Questions to Stephen?
You never show an example with a loop or recursion. Is it because you have a problem for under approximation and proof terminations, or you don't like iterations?
Yeah, so if I understand correctly, you asked me that I don't show any example about loop or recursion. And
Why?
if that's a problem, no. I mean, in order to prove this coverage or the reachability, all this loop must be terminated. So my type system will do the check to guarantee all this loop will be terminated, just like how we do that in COG. We have some well-founded relation on the loops or recursion.
Okay, so you have a method to prove termination.
Yeah.
Okay, great. And you can explain this method?
Can you finish that?
Which method do you use to, that is, you say I have a well-founded order, okay?
Yeah.
How do you find it?
Oh, so our type system requires this, we have some universal built-in well-founded relation for this basic type, and the data types is a structural decreasing order.
So you have predefined order that you try, and if you are not in that case, what do you do?
Yes, like all possible verification tool. If I cannot prove it, I can see nothing.
It's not typeable, okay.
Yeah, thanks for the talk. So I don't quite understand the tagline, well-typed programs must go wrong. But is it not the case that you can type an expression with a function type, but it doesn't necessarily go wrong?
So we say, if I understand it correctly, you say you don't, you have, your question answers my statement, well-typed program must go wrong, especially for the functions, right?
That's right, yeah.
So what do we mean we go wrong is that in some sense, the function itself never go wrong. It's go wrong when the function application in some case. And in order to say that in the future, the function go wrong, we actually say that some reachability property for this function. In that sense, if it proves the bad reachability property for this function implementation, we say the function is somehow go wrong in the future. I don't know if that satisfies this answer.
Yeah, that makes sense.
Okay.
Thanks.
Any other questions for Giorgio? Okay, let's thank him again.
Okay, thank you. Oh, yeah.
Thank you. Hello. Yeah. I can check if it's shown there.
Does your laptop have USB-C? Because that seems to be the dongle. It seems to be working. This one has been working.
This one.
Yeah? This is the one we've been trying, yeah?
This one doesn't have page.
Where is it? Oh, no, that's too small. How does that leave it if you like?
Can you maybe send the slides to someone?
This is just a PDF. Yeah, this is a PDF. Okay. Let's try. The ironic thing is that this is the Institution of Engineering and Technology, and the technology seems to be completely bust in every room I've been. It's amazing.
Since down the engineers, we can't trust them.
Yeah, goes to show. Yeah.
Yeah, I know. Should have more researchers in, plugging cables and things. Should have more research in plugging cables.
It seems to like Mac, so hopefully this should be okay. But it has HDMI, and it has USB-C. Oh, well, you can plug it in here. Let's see. Anything? Yeah. Okay. It should show you here. No, here. Maybe copy it locally. I don't know. Leave it. Let's not mess with it. And now you need to go to settings. Well, do you think? Get full screen. This is fine, no? Yeah. I think it is. There you go. Of course. Oh, it's skipping. Okay. Okay. Wait. It's doing that. Wait. Better. Yeah, it's Command Shift F is presentation mode. Command Control F.
Test. Yep.
Take it away. Thank you.
Okay. So today we've heard a lot about imperative languages and Hoare-like logics to do with bug finding and incorrectness. But I'm going to talk about functional programming and types, so another outlier in this event. So of course, the core of a functional language is the lambda calculus. So we have there our abstraction, application, and variables. And for some more interesting examples, I'm going to add ADTs and pattern matching. The types that I'll be concerned with, we have our type variables, the arrow type for our ADTs and pattern matching. I'll also include constructor types and sum types. And I'll also add on a top type at the end, so all values will be a member of this OK. If you're unfamiliar with constructor types, they're a nice way to type our constructors. So nil, the empty type, is a constructor itself, and so it can be typed at nil. The list containing only one can be typed at cons nat nil, but of course both of these can also be typed at list of nat. Typing judgments, as I'm sure you all know, take this form for just about any type system that you're concerned with. You'll be proving judgments of this form. where we have a list of variable typings on the left, and then we have some term that we're interested in being typed on the right. We can then interpret this, at least informally, in this manner, where if we have that all of our variables sit inside their respective types, then our expression must sit in our B type or diverge. But of course, this doesn't tell the whole story and doesn't do everything we want, otherwise we wouldn't be here talking about incorrectness. So one of the simplest bugs that you can have is that the program just crashes. So one way that we can encode this is by saying that a given expression E is not in this top type OK. This is because if E does not evaluate to a value, then it must either crash or diverge. But clearly this is a negative statement, which doesn't look anything like what we already know. If we try and write this as an implication, we end up with this, which is closer, but we still haven't gotten into a form that we can use with typing judgments. So if we, again, take some general typing judgment from any type system, we can make some observations on some restrictions on this judgment that are stopping us from modeling this implication that we want. So the first is that only variable typings can occur on the left. We had an arbitrary expression being typed to OK on the left with our implication, but we don't allow that with our typing judgment. The second is a bit more subtle, but there must be exactly one typing in the conclusion. We wanted false in our conclusion, which isn't a typing, it's a more meta value. So let's just relax these restrictions and examine the form of these judgments afterwards. So both of these forms can technically be summed up in the first one, but the second one is more interesting for bug finding and incorrectness. So as you can see, on the left, rather than simply variables, we allow arbitrary expressions to be typed in the context. And on the right, we either allow some list of expression typings on the right, which may or may not be empty. Now it's great writing this down, but what do we actually mean by this? Well, let's look back at our logic. So again, if all of the expressions on the left are in their respective typings, then at least one of the typings on the right-hand side is in its type or diverges. And if there are no typings on the right, then there isn't a typing that can be satisfied, and so we have false. So let's look at some examples and see if we can actually see what we can write this, see if we can model our desired implication. So the first example is a simple right-handed one. So we still have all of the theory and results over decades on correctness logic. This is simply a reminder on how you may use types to describe properties, more complex properties of a function. So here this is saying that if you give the map function a function that maps natural numbers greater than 3 to natural numbers greater than 8, and you also give map a list of natural numbers greater than 3, then it will apply the function to every element in the list, and it will produce you a list of natural numbers greater than 8. So for the rest of this presentation, I use quite simple types, but you can just as equally replace the simple types with more interesting properties. So example 2 actually uses our two-sided system, to describe some reasoning that you may use while you're programming. So number 2 can be read as if x plus 1 evaluates to a natural number, then the identity function applied to x evaluates to a natural number. This is follows the natural reasoning that you'd have of if x plus 1 is a natural number, then x must be a natural number. The identity function simply returns the argument it's given, and so the identity function applied to x must return the natural must evaluate to a natural number. Number 3 gives us our first example of negative reasoning. So you can read this as the empty if the empty list evaluates to a natural number, then false. That is, this is saying that the empty list is not a natural number. Now for a more clear example of bug finding and incorrectness. Fourth example says that if 1 plus the empty list evaluates to a value, then false, i.e. that 1 plus nil either crashes or diverges, but clearly doesn't diverge. And then number 5 follows very similar reasoning to number 4, but simply uses some pattern matching. But how do we derive or prove these judgments? Well, as usual, we use typing rules. So the typing rules at the top are standard typing rules that you can look up in just about any lambda calculus textbook. But we've sprinkled some deltas on the right-hand side, which are simply the typings on the right that you aren't interested in for this particular instantiation of the rule. The 2 rules on the bottom are some left-handed examples. So the first one is refuting that a constructor is typed at a given constructor type. Following through the reasoning, if you want to refute that a constructor with some arguments is typed at the correct constructor type with some types for its arguments, then as the constructor type, the outermost constructor is correct for the type, it must be that there exists some argument to this constructor that has been given the wrong type. The match L rule on the bottom, this rule has been both simplified and specialized, so there are most likely some cases that there may be ways to refute a typing for match that are not covered by this rule. However, following through the reasoning of this rule here, we look at the branch PS that would evaluate if match produced something of a successor, and we try and extract information from this branch about what the type of the free variable x must be. As in our pattern match, we have this free variable x in successor, and we just want to try and find what type PS requires that x to be. And then in the other 2 premises, we simply try and type E at the branch's type, but with the free variables replaced by the required types that we know. So, interestingly, if it may not be the case that E produces something of both types, so if, for example, E never produced something of type 0, you would be able to extract that information from the second premise and refute that typing. However, in the third premise, if E did produce something of shape successor, you wouldn't be able to refute that typing, and instead you would have to prove something in delta from the information that you can gain from the given typing. So we're going to take a slight side tangent and talk about a new arrow type necessity, which will be needed for the left-hand rule for application. So this is how we write this necessity arrow, and we read it A only to B. Since it's an arrow type, we already have an arrow type, so let's compare it to something that we already have. So we have sufficiency on the left, which is our standard arrow type. We have the two rules where they have a nice symmetry in the premise where the E and the X have been swapped around. So if we go through the examples to try and build some intuition here, the first example of sufficiency, with lambda x dot 42, if you give it something of type nat, then it will give you back something of type nat. That is, if you wish to receive a nat from this function, it is sufficient to give it a natural number, but of course you could give it something outside of nat. With map f, if you give it the empty list, it will give you back the empty list. But of course you can expand the codomain of that type. If you give it the empty list, then it will produce the empty list, but the empty list is obviously a list of alpha, and so it can also be given this type. However, as we know, it would be incorrect to give map f this list of alpha to the empty list type. With necessity, we're looking more at pre-images than images. So with the first example, the head function, if you want to get something of type alpha out of this function, then you are required to give an argument of the shape cons alpha OK. Now, the OK is important here because the head function places no requirements on the second argument to the cons. With map f, if you want to get the empty list out, then you are required to give the empty list. However, we do also allow elements from the domain of our arrow to not map to the codomain in a forward reasoning style. Similar to how in sufficiency, we allow elements in the codomain to not be mapped to from our domain. So with map f, if you want to get the empty list out, then you are required to give it something of list A. But this type is not the most strict type that you could give it. But it would be, for our last example here, it would be incorrect to give the lambda x dot 42 the type nat only to nat, because there is no requirement by this function for its argument to be a natural number. As I said before, you can give this the empty list and it will still produce a natural number. So now we can return to application on the left. So you can see here that if you wish to refute that an application has a given type, then first you need to show that the function part of that application requires that the argument, if you want to produce a B, the argument is required to be in type A. But then you also show that the argument that you're actually giving it is not in this type A. And so now that we have application on the left, we can actually show interesting examples of finding bugs. So the classic would be giving the empty list to head. So the head function, if you want a value out, then you have to give it an argument of shape cons okay, okay. And of course, nil is not a cons-like thing. And thus, we've proven that head of nil does not evaluate. That is, it doesn't reach a value. So, in conclusion, by using this two-sided framework to our typing, we maintain all of the results over the past decades on well-typed programs by typing on the right, as we always have. However, we can also, if we can type a program at OK on the left with no conclusion, then we can prove that it will not evaluate to a value. And as this is a special case with practical applications, we've decided to call this particular case that we say that E is ill-typed. And thus we can have the tagline, ill-typed programs don't evaluate. Thank you.
Thank you, Charlie. It's never easy to be the last talk of the day. Thanks again. Any questions for Charlie? Patrick.
I have not understood how you handle recursion, because you have no recursion operator, and your type system cannot type combinators.
So in the full paper, we do have fixed points. So we do have recursion, and that does play well with the system. I've just not included it on the slides for simplicity. So we can still type fixed points on the left. Applications and fixed points are sort of a special case. You can create a specialized rule for them, but they involve inventing a value to show that its property is incorrect. The way that we actually use it in practice is through a axiomatization of disjointness between two types. So if you want to refute that, for example, head is a nat to nat function, then you instead affirm that it has some other type that is disjoint from nat to nat. And then a similar result for, similar rule for fixed points.
You don't have to prove either non-termination and termination to conclude? That's surprising.
So for call by value, you don't have to talk about termination at all. For call by name, you do have to talk about termination of various things, and so the call by name system is significantly weaker than the call by value system. But for a call by value type system, you don't have to talk about termination.
Are there many programs in the middle that neither are well-typed nor ill-typed?
Yes, there are. So there are programs that are neither. That is almost certainly how we're getting around talking about termination. Interestingly, there are actually programs that sit in the intersection that are both well-typed and ill-typed, and they would be divergent programs. So the fixed point of the identity function is both well-typed and ill-typed. I don't know if we have a proof for it, but I believe that only divergent programs can sit in its intersection.
You mentioned using it in practice. Do you have an implementation of type checking or type inference or anything?
So we have type inference, an algorithm for type inference. It hasn't been implemented, but there is an algorithm in the appendix for type inference. It uses, so it's completely automated and uses standard techniques. There is very little interaction between the two sides. But as a given term does not have a unique typing, we work with sets of types, or in the case of the Edgewell algorithm, sets of judgments, because you need to keep track whether a given type is proved on the left or the right. But we do have type inference for the system.
What do you understand as go wrong? Because if you over-approximate, you divide by 0, it doesn't go wrong. And when you under-approximate, you divide by 0. Does it go wrong or not?
So we define go wrong by does not evaluate to a value.
Okay.
So as for under and over approximate, the necessity arrow that I've been talking about is roughly necessity logic in the whole-like logics. So it's a functional representation of the necessity triples.
Okay, let's thank Charlie again. Oh, well, is there another question? Okay. Right, thank you all so much for coming and making the Incorrectness workshop happen. It's really lovely to see how much the area has already flourished in the short space of 4 years. So let's have a round of applause for our speakers and for our attendees, for all of you. I also would like to thank my co-organizer, Noam. And I say co-organizer, but I should admit that my role as the co-organizer was mostly nominal. Noam took care of everything. So the next time you want to organize a workshop, find an overachieving grad student and let them do all the work. So let's thank Noam. And finally, can I have a round of applause for our student volunteers putting up with all the AV issues? Thank you. And you can go.
Oh, wait. Let's have a round of applause for Azalea and Noah.